Right now, the nearest star beyond our sun is so far away that if you had boarded a spacecraft on the day the first human being walked upright on the African savanna, you would still be traveling. You would not have arrived yet. You would not even be close. That star is called Proxima Centauri. It is a small, dim red dwarf burning quietly in the constellation Centaurus, visible only from the southern hemisphere, unremarkable in almost every way except for one. It is our closest stellar neighbor in the entire galaxy, and it sits 25 trillion miles from where you are sitting right now. 25 trillion. The number is so large that the human mind, shaped by hundreds of thousands of years of evolution on a single small planet, simply refuses to process it honestly. We read the words, we recognize them as representing something enormous, and then we move on, because there is no frame of reference in daily experience that makes 25 trillion miles feel real. So let me try to make it feel real, because what comes after depends entirely on you understanding, in your bones, just how catastrophically far away the stars actually are. Light travels at roughly 186,000 miles per second. In the time it takes you to blink, a photon of light has already crossed the entire continental United States twice over. In 1 second, that same photon could circle the Earth at the equator 7.5 times. In 8 minutes, it reaches the Sun from Earth. In about 43 minutes, it reaches Jupiter. In roughly 5.5 hours, it crosses the entire solar system and passes beyond the orbit of Neptune, the outermost planet. And then it keeps going. For 4 years and 3 months, through absolute emptiness, through a vacuum so cold and so silent that no human language has an adequate word for it, the light travels. 4 years and 3 months at 186,000 miles per second, before it finally arrives at Proxima Centauri. That is how far away our nearest neighbor is. 4 light years, 25 trillion miles. A distance so vast that the fastest thing permitted by the laws of physics requires more than 4 years to cross it. Now consider what we have actually built. Voyager 1 was launched on September 5th, 1977 from Cape Canaveral, Florida. It has been traveling continuously for nearly half a century. It is currently the most distant human-made object in existence, having crossed the boundary of the solar system in August 2012 and entered interstellar space. It is still out there right now, still transmitting data across billions of miles of emptiness, still functioning on power generated by the decay of plutonium-238, its signal growing fainter with every passing year. Voyager 1 is moving at approximately 38,000 miles per hour relative to our Sun. That is fast by every measure that matters to human beings. A commercial airliner cruises at around 600 miles per hour. A bullet fired from a high-powered rifle travels at roughly 2,000 miles per hour. Voyager 1 is moving 19 times faster than that bullet, continuously, without slowing, through the void between the stars. And, at that speed, it would take approximately 70,000 years to reach Proxima Centauri. 70,000 years. When Voyager 1 finally drifts close enough to that star for the word approaching to carry any meaning, our species will have existed for longer than we have existed now, since the first anatomically modern human beings walked the Earth. The pyramids of Giza were constructed roughly 4,500 years ago. The entire recorded history of human civilization, every war, every empire, every invention, every philosophical tradition, every piece of music ever written, spans about 5,000 years. Voyager would need to live through 14 of those spans, stacked end to end, before it reached even the nearest star. And Proxima Centauri is the closest one. Sirius, the brightest star in our night sky, sits 8.6 light-years away. At Voyager's speed, reaching it would take roughly 150,000 years. Betelgeuse, the red supergiant, marking the shoulder of Orion, glows at a distance of about 700 light-years. A Voyager-class probe aimed in that direction would not arrive before our own Sun had exhausted its hydrogen fuel and begun the process of expanding into a red giant, eventually swallowing the inner planets, including Earth. The galaxy contains somewhere between 200 billion and 400 billion stars. Nearly all of them are, for all practical purposes, permanently beyond our reach. This is the prison of distance, and for most of human history, it seemed absolute. The engineers who came after the early pioneers of rocketry understood the problem clearly. The issue was not that our engines were insufficiently powerful. The issue was the fundamental physics of how rockets work, and a mathematical relationship so brutal it has been given a name: the tyranny of the rocket equation. Every rocket ever built operates on the same principle. You carry fuel, you burn it. The exhaust, rushing backward, pushes the vehicle forward. Newton's third law, action and reaction, simple and elegant in concept, devastating in practice when applied to the challenge of reaching another star. The problem is mass. Fuel has mass, and that mass must be accelerated along with the spacecraft, which means you need additional fuel to move the fuel, which itself has mass, which requires even more fuel to accelerate. The relationship is not linear, it is exponential. As the desired velocity increases, the required fuel mass does not merely increase proportionally, it explodes upward in a curve that eventually reaches values beyond any physical possibility. Consider the Saturn V rocket, the vehicle that carried human beings to the moon during the Apollo program. It stood 363 feet tall and weighed, fully fueled, approximately 6.5 million pounds at launch. Of that total mass, roughly 85% was propellant. Fuel and oxidizer, kerosene and liquid oxygen consumed in the first few minutes of flight. All of that mass, all of that engineering, all of that fuel burned in under 3 minutes to push a tiny capsule containing 3 human beings 250,000 miles to the moon and back. Proxima Centauri is 100 million times farther away than the moon. If you attempted to scale a chemical rocket to reach Proxima Centauri within a human lifetime, the calculation produces numbers that cease to correspond to anything real. You would need fuel reserves exceeding the total mass of hydrocarbons available on Earth. Every oil deposit, every natural gas field, every organic compound on the planet, stripped away and burned, would not come close to providing what the rocket equation demands. You would need to harvest the atmospheres of Jupiter and Saturn. You would need to dissolve every asteroid and comet in the solar system into fuel, and still, the numbers would not balance. Chemical propulsion is not the path to the stars. It never was. It cannot be. Engineers recognized this decades ago, which is why every serious proposal for interstellar travel has attempted to sidestep the rocket equation entirely, or at least find a different version of it to obey. Nuclear pulse propulsion was one of the first serious ideas. Developed in the late 1950s and early 1960s under a classified American program called Project Orion, the concept involved detonating nuclear bombs in rapid succession behind a massive spacecraft. Each explosion would push against a thick steel plate connected to the ship by shock absorbers, driving the vehicle forward in a series of controlled impulses. The physics worked. Nuclear explosions release energy roughly 1 million times more efficiently per unit mass than chemical combustion. A ship powered by nuclear pulse propulsion could, in theory, reach several percent of the speed of light. At 3% of light speed, the journey to Proxima Centauri shrinks from 70,000 years to about 140 years, still longer than a human lifetime, but a generational ship could make the voyage. The practical obstacles were extraordinary. The program would require thousands of nuclear warheads. The launch from Earth's surface would be environmentally catastrophic. The political and legal barriers, in a world where nuclear weapons are controlled by international treaty, are almost certainly insurmountable. Project Orion was cancelled in 1963 following the Partial Nuclear Test Ban Treaty, and it has never been revived in any serious way. Fusion propulsion represented the next step in ambition. Instead of fission, the splitting of heavy atoms, a fusion drive would burn hydrogen the way stars do, forcing light nuclei together and extracting the energy of the resulting reaction. Fusion is more efficient than fission and produces less radioactive waste. A fusion rocket could theoretically reach 10 or even 20% of light speed, reducing the journey to Proxima Centauri to a few decades. Still a long voyage, but one that a single human being could survive. The problem is that humanity has been attempting to achieve controlled nuclear fusion in stationary power plants on Earth for more than 70 years, and it remains one of the most difficult engineering challenges ever attempted. Building a fusion drive that operates reliably in the vacuum of space, under the thermal and mechanical stresses of continuous operation, while accelerating to a significant fraction of light speed, is a problem that makes the terrestrial fusion challenge look straightforward by comparison. Antimatter propulsion represents the theoretical ceiling. When a particle of matter meets its antimatter counterpart, both are annihilated completely. 100% of their combined mass is converted into energy, as Einstein's equation E equals mc squared describes. No reaction in nature is more efficient. An antimatter rocket could theoretically accelerate a spacecraft to a significant fraction of light speed on quantities of fuel that would fit inside a small room. The catch is that antimatter does not occur naturally in useful quantities anywhere we have found. Every antiproton, every positron, every atom of antimatter must be manufactured in particle accelerators at an energy cost that dwarfs the energy it will eventually release. The current global production rate of antimatter is measured in nanograms per year. Building a fuel supply sufficient for an interstellar mission would require production rates billions of times higher than anything we have achieved, sustained over periods of decades, at energy costs that would exceed total global power generation, and storing the resulting antimatter without it contacting ordinary matter and exploding is an engineering problem nobody has solved. The Breakthrough Starshot initiative, announced in 2016 with funding from the Russian entrepreneur Yuri Milner and the support of physicists, including Stephen Hawking before his death, proposed something different. Instead of propelling a large crewed spacecraft, the concept calls for accelerating tiny probes, each no heavier than a few grams, using pressure from powerful ground-based laser arrays. The probes would carry light sails, thin reflective sheets of material that would be pushed by the concentrated light beam the way a sailboat is pushed by wind. If the lasers could deliver enough power, the tiny probes could be accelerated to 20% of the speed of light. At that velocity, they would reach Proxima Centauri in approximately 20 years and could transmit data back using onboard lasers. The concept is scientifically plausible, and the physics is real, but it applies only to gram-scale probes. Scaling a laser sail to push a spacecraft containing human beings would require a sail hundreds of miles across, and a laser array whose power output would represent a significant fraction of all electricity generated on Earth. It does not scale to crewed missions. Each of these approaches claws a little closer to the stars. Each one is a genuine achievement of human ingenuity, pushing against the boundaries of what physics allows, but none of them breaks the ceiling. None of them solves the deeper problem. The deeper problem is not fuel efficiency. The deeper problem is the speed of light. The speed of light is not simply the fastest speed we have achieved. It is not a record waiting to be broken by better engineering or more powerful engines. It is a fundamental constant of nature, woven into the geometry of space and time itself. And the story of how we discovered this, and what it truly means, is one of the most important stories in the history of human thought. In 1905, a 26-year-old patent clerk in Bern, Switzerland, published 4 papers that would collectively transform physics more thoroughly than any work since Newton. His name was Albert Einstein. He had no university position. He had been unable to find an academic job after graduating. He worked days evaluating patent applications and spent his evenings and weekends thinking about the deepest problems in physics. One of those papers, published in June of that year, introduced what would become known as the special theory of relativity. The paper was titled, in German, On the Electrodynamics of Moving Bodies, and it began with a deceptively simple observation. The laws of physics should be the same for all observers moving at constant velocity, regardless of how fast they are moving relative to each other, and the speed of light should be the same for all of them. This second condition seems innocuous. It is not. If the speed of light is constant for all observers, then the measurements of space and time cannot be. 2 observers moving relative to each other must disagree about distances and durations in order to agree about the speed of light. Time itself must flow differently for different observers. Space itself must contract or expand, depending on relative motion. These are not metaphors. They are physical realities, confirmed by experiment thousands of times in the century since Einstein wrote that paper. And from this foundation, a consequence followed that sealed the fate of any conventional approach to interstellar travel. As any object with mass accelerates toward the speed of light, its effective mass increases. Not its rest mass, the mass it has when sitting still, but its inertial mass, its resistance to further acceleration. The faster it moves, the harder it becomes to push it faster still. At 10% of light speed, the mass increase is barely detectable. At 90%, the effective mass has grown to more than twice its rest value. At 99%, it is 7 times heavier. At 99.9%, 22 times heavier. To actually reach the speed of light would require an infinite amount of energy, because the effective mass becomes infinite at that velocity. Infinite energy does not exist. It cannot be stored, cannot be released, cannot be applied. Therefore, nothing with mass can reach the speed of light. This is not an engineering limitation. It is not a problem that a better rocket engine will solve. It is not a barrier that will yield to more advanced materials or more efficient nuclear reactions. It is a property of space and time themselves, as fundamental as the fact that parallel lines do not meet on a flat surface. The speed of light is the maximum rate at which any causal influence can propagate through the universe. To exceed it would not merely be fast. It would be, in a precise mathematical sense, to travel backward in time, to violate causality, to arrive before you departed. The universe does not permit this. Or so every physicist believed, with complete confidence, for nearly 90 years after Einstein wrote those words, until a young researcher in Wales decided to ask a different kind of question entirely. But before we get to that moment, before we enter the physics that changed everything, there is something you need to sit with. Take a moment to feel the full weight of what has just been established. Every star you have ever seen in the night sky is unreachable. Not difficult to reach, not expensive to reach. Unreachable in any practical sense, by any technology that obeys the laws of physics as we understand them. The universe has given us eyes that can see billions of light years in every direction, and laws that confine us to a single star system. It has shown us a cosmos of incomprehensible richness and beauty, and then, with the same mathematics, informed us that we cannot go there. That is the prison, that is the full weight of the distance problem. If you find yourself drawn into questions like this one, into the deepest structures of the universe and what they mean for the strange, brief creatures that evolved to notice them, then consider subscribing to this channel. Every exploration we make here begins exactly where this one does, with a question that seems unanswerable, and a commitment to following the physics wherever it leads, however far that turns out to be. It genuinely helps this channel reach more people who want to think about these things seriously. Now, we have established the cage. Now we understand exactly why the stars seem permanently beyond reach. Let's begin. In 1994, a 28-year-old theoretical physicist named Miguel Alcubierre was working at the University of Wales in Cardiff. He had trained at the National Autonomous University of Mexico, completed his undergraduate work with distinction, and moved to Europe for postdoctoral research. By all conventional measures, he was exactly the kind of careful, rigorous physicist that the academic world produces and expects. He thought precisely. He respected the established boundaries of the field, and he watched Star Trek. Star Trek, for those who encountered it only as cultural background noise rather than as something watched with genuine attention, is a science fiction television series that first aired in 1966. The show depicted a future in which human beings traveled between star systems aboard vessels called starships, crossing distances of light years in days or weeks, using a technology the characters referred to as warp drive. The ships would accelerate to warp factor 1, warp factor 5, warp factor 9, and the stars outside the viewports would blur and streak as the vessel leapt between solar systems as casually as a commercial aircraft crossing an ocean. The show never explained how warp drive worked. It did not need to. It was fiction. The writers invented the name, gave it a vaguely technological sound, and moved on to the stories they actually wanted to tell. Most physicists who were aware of the concept dismissed it without serious thought. Einstein's equations said faster-than-light travel was impossible. The show was fantasy. End of analysis. Alcubierre decided to treat it as a homework problem. He sat down with Einstein's field equations, the mathematical foundation of general relativity, the theory that describes gravity, not as a force pulling objects together, but as a curvature of space-time caused by the presence of mass and energy. These equations, first published by Einstein in November 1915, are among the most beautiful and demanding objects in all of mathematics. They relate the geometry of space-time on one side of the equation to the distribution of matter and energy on the other. Change the matter, change the geometry. Change the geometry, change how everything within it moves. Alcubierre asked those equations a very specific question. What shape would space-time need to have for a region inside it to move faster than light, without any object within that region actually exceeding light speed? At first reading, this sounds like a contradiction, moving faster than light without moving faster than light. But Alcubierre had identified something subtle, something that had been present in Einstein's equations since 1915, and that nobody had seriously pursued in this context. A loophole. Not a violation of the rules, but a gap in them. A distinction that the equations themselves drew clearly, even if no one had thought to look at it this way before. Einstein's cosmic speed limit applies to objects moving through space-time. A rocket accelerating through space, a particle fired through a collider, a radio signal propagating through the vacuum. All of these are things moving through the fabric of the universe, and for all of them, the speed of light is an absolute ceiling that cannot be approached, let alone crossed. But Einstein's equations also describe something else entirely. They describe how space-time itself can change shape, how it can curve around a massive object, how it can stretch or compress, how it can expand. And, crucially, there is no speed limit on that. We know this because we can observe it happening right now at scales that dwarf anything in human experience. The universe is expanding. The space between distant galaxies is stretching, carrying those galaxies apart from one another, the way dots drawn on the surface of a balloon move apart as the balloon is inflated. The galaxies are not moving through space at those velocities. The space itself is growing, and the galaxies are embedded in it, carried by the expansion the way objects floating on the surface of a river are carried by the current without swimming. And at sufficient distances, roughly 46 billion light-years from Earth in every direction, that expansion is carrying galaxies away from us faster than the speed of light. Not because those galaxies are violating Einstein's laws, not because anything within them is moving at superluminal speed, but because the space between us and them is growing faster than light can cross it. The metric, the mathematical description of distance in that region, is changing at a rate that exceeds the speed of light. And nothing in Einstein's equations forbids this. This is called metric expansion. It has been confirmed by decades of astronomical observation, most precisely by studies of the cosmic microwave background, the faint afterglow of the Big Bang, and by measurements of the redshift of distant supernovae. The universe is unambiguously doing this. Space itself moves faster than light. It does so routinely. It has been doing so since the earliest moments of cosmic history. Alcubierre looked at this loophole and asked the obvious question that no one had thought to ask before. If space can carry galaxies apart at faster than light velocities, could it carry a spacecraft? Could you engineer a local region of space-time to compress in front of a ship and expand behind it, creating a wave in the geometry of space itself, and allow the ship to surf that wave to any destination at any speed, without the ship ever moving through space at a velocity that violates Einstein's limit? He worked through the mathematics with great care. General relativity describes space-time using a mathematical object called a metric tensor. The metric is, in essence, a recipe for calculating distances and time intervals in a given region. Different configurations of matter and energy produce different metrics. The metric around a non-rotating star is called the Schwarzschild metric, and it describes how mass curves space-time into what we experience as gravity. The metric around a rotating black hole is the Kerr metric, and it describes the more exotic twisting of space-time caused by angular momentum. Alcubierre constructed a new metric, a metric that describes something nobody had written down before: a bubble. The interior of the bubble, the region where the spacecraft sits, has a flat metric. Space-time inside the bubble behaves normally in every way. Clocks tick at standard rates. Light moves at its standard speed. An astronaut inside would feel no unusual forces, no acceleration, no gravity, no distortion of any kind. The laws of physics would operate exactly as they do in the room where you are sitting right now. Nothing inside the bubble would be moving at a superluminal velocity relative to the local space-time around it. Outside the bubble, far from the ship, the metric is also flat. The surrounding universe behaves normally, unaffected by what is happening at the bubble's location. But at the boundary of the bubble, at the thin shell where the interior transitions to the exterior, the metric does something remarkable. On the leading edge, the front of the bubble, as it moves toward its destination, space-time contracts sharply. Distances compress. The metric components change in a way that squeezes the space immediately ahead of the bubble, drawing the destination closer. On the trailing edge, the back of the bubble, space-time expands just as sharply. Distances stretch out behind the ship, pushing the origin point further away. The bubble itself rides this geometry forward. From the perspective of a stationary observer watching from outside, the bubble translates through space at whatever velocity you have chosen. If you have configured the metric correctly, that velocity can be 10 times the speed of light, 100 times, 1,000 times. The mathematics does not object. From the perspective of the astronaut inside, nothing is moving at all. The ship is stationary relative to its immediate surroundings. It is the universe outside that is rearranging itself, the geometry reshaping so that the destination comes to the ship rather than the ship traveling to the destination. The ship does not accelerate. It does not gain kinetic energy in the traditional sense. The crew does not feel any G-forces because they are not being pushed. They are sitting in a pocket of flat space-time that happens to be changing its position in the larger universe, the way a leaf resting on the surface of a stream is carried forward by the current without the leaf itself moving relative to the water immediately surrounding it. Alcubierre published his result in May 1994 inches, the journal Classical and Quantum Gravity. The paper was 8 pages long. Its title was The Warp Drive, Hyper, Fast Travel Within General Relativity. And when it appeared, the physics community experienced something it rarely does: genuine surprise. The surprise was not that someone had proposed faster-than-light travel. Speculative papers appear in physics journals regularly. The surprise was that the mathematics was unambiguously correct. Alcubierre had not made an error. He had not hidden a trick inside a complicated derivation. He had written down a valid solution to Einstein's field equations, a space-time geometry that described a region moving faster than light, in full consistency with the laws of general relativity, without any local violation of the speed limit anywhere within the structure. Einstein's equations did not forbid this. They described it. The excitement spread quickly through the theoretical physics community. Here was a proof, not a speculation but a mathematical demonstration, that faster-than-light travel was not strictly forbidden by the fundamental laws of the universe. The equations that had seemed to seal the door had, it turned out, left a gap. A narrow gap. A gap that came with severe requirements, but a gap nonetheless. To understand why the gap came with severe requirements, you need to understand what holds the warp bubble together. The bubble does not maintain its shape on its own. The compressed region in front and the expanded region behind require something to create and sustain them. In general relativity, space-time geometry is produced by matter and energy. The curvature of space around the Earth is produced by the Earth's mass. The extreme curvature near a black hole is produced by the black hole's mass. The curvature of the warp bubble, the compression and expansion at its boundary, also requires matter and energy to maintain it, but not ordinary matter. The compression and expansion of the warp bubble's boundary curves space-time outward, repulsively. Ordinary matter, the kind that makes up everything you have ever touched, or seen, or measured, curves space-time inward. That is what gravity is. Mass curves space inward, and objects moving through that curved space follow paths that bring them together. To curve space-time outward, to create the repulsive geometry the warp bubble needs, requires something different. It requires matter with negative energy density. Negative energy. The concept sounds like science fiction, and in daily experience it is. You have never encountered a substance that falls upward. You have never held an object that pushed other things away, gravitationally. Negative energy, if it exists at all in the form a warp bubble requires, is not part of the ordinary inventory of the universe. Protons have positive energy. Neutrons have positive energy. Photons have positive energy. The vacuum of empty space, according to quantum field theory, has a small positive energy density from the constant churning of virtual particles that exist and vanish at the quantum level. Negative energy is something else entirely. And in Alcubierre's original design, the warp bubble required enormous quantities of it. The first researchers who worked through the energy calculations came back shaken. The amount of exotic matter required to sustain the bubble was not large in the way that very expensive is large, or technically challenging is large. It was large in the way that defies any engineering intuition. The estimates converged on a number roughly equivalent to the total mass energy of the entire observable universe, every star, every galaxy, every particle of dust, in every direction out to the cosmic horizon, all of it converted into negative energy and arranged in a shell around a single spacecraft. The number was so catastrophic that many physicists assumed an error had been made somewhere in the calculation. The calculations were checked. They were not wrong. The original Alcubierre metric, beautiful as it was, required exotic matter in quantities that bore no relationship to any conceivable engineering program. It was a proof of concept in the most abstract sense. The geometry worked, the physics permitted it, the energy requirement made it, for all practical purposes, indistinguishable from impossible. And yet, the physics community did not entirely walk away. Because the energy requirement was not a fundamental no-go theorem. It was not a proof that warp drive was impossible. It was a calculation based on a specific choice of geometry, specifically the shape and thickness of the bubble's boundary region. Different geometries produced different energy requirements. The question was whether a cleverer choice of shape could bring the number down to something less cosmological in scale. In 1999, a physicist at the Free University of Brussels named Chris van den Broek published a paper that answered that question with a result that startled even the specialists working in the field. Van den Broek had been studying the relationship between the exterior size of the warp bubble and its interior size. In ordinary flat space, these are obviously the same. A sphere that looks 1 meter across on the outside contains 1 cubic meter of space inside. But in curved spacetime, that relationship can be decoupled. General relativity permits geometries where a small exterior volume contains a vastly larger interior space. The classic example is a wormhole, where a mouth the diameter of a door could theoretically open onto a tunnel stretching light years in length. The interior and exterior dimensions are separated by the curvature of the geometry. Van den Broek applied this insight to the warp bubble. He proposed shrinking the bubble's exterior to an almost incomprehensibly small scale, on the order of 10 to the negative 15 meters. That is approximately the diameter of an atomic nucleus. A proton is roughly 1 femtometer across, and Van den Broek's bubble would have an outer radius comparable to that. From the outside, the bubble would be microscopic, smaller than any atom, invisible to any instrument except the most exotic particle detectors. But the interior of the bubble, protected by the curved geometry connecting inside to outside, would be normal in size, large enough to contain a spacecraft and its crew, operating under the familiar flat space-time of the passenger region, experiencing no unusual conditions. The mismatch between interior and exterior volume is not a paradox in general relativity. It is a feature of the mathematics. The curvature of the boundary region handles the transition between the two scales. By making this change, Van den Broek reduced the exotic matter requirement by more than 20 orders of magnitude. 20 orders of magnitude. That is a factor of 100 billion billion. the energy requirement fell from something comparable to the mass of the observable universe to something closer to the mass of Jupiter. Jupiter contains roughly 2 trillion kilograms of mass. That is still an extraordinary quantity of matter, still far beyond any engineering program imaginable, still in a category that might reasonably be called impossible. But it is a different category of impossible than the previous calculation. The original Alcubierre metric required the entire universe. Van den Broek required one large planet. The problem had moved, not into the realm of the achievable, but into a realm where the word achievable could at least be used in the same sentence without provoking immediate laughter. The physics community treated Van den Broek's result as genuine progress. Papers continued to appear. A physicist named José Notario proposed a variant in which the bubble experienced no compression or expansion at all, relying instead on a tangential flow of spacetime around the ship, the way water flows around a rock in a river. Notario's design avoided some of the original Alcubierre problems, but introduced different ones. Other researchers examined stability conditions, asking whether a warp bubble, once formed, would maintain its shape or collapse catastrophically under small perturbations. The field was maturing slowly, refining its understanding of what was required and what was possible. And then, in 2011, a NASA engineer walked into the conversation with a redesign that reduced the energy requirement by another extraordinary factor, and the mainstream scientific press began paying attention for the first time. Harold White worked at NASA's Johnson Space Center in Houston, Texas, in a division called the Advanced Propulsion Physics Laboratory, informally known as EagleWorks. EagleWorks was the part of NASA where engineers could pursue ideas that existed at the boundary between established physics and speculation. Warp drive, wormholes, alternative propulsion schemes rooted in real mathematics but requiring breakthroughs that had not yet been made. It was, within the bureaucratic structure of the world's most prominent space agency, the room where people were allowed to ask the difficult questions. White had spent years studying Alcubierre's mathematics. He understood the energy requirements in detail, and he believed that the shape of the bubble boundary, the transition region where space-time shifted from compressed to expanded, had not been optimized. Previous researchers had focused on thin boundaries, sharp transitions where the metric changed steeply over a short distance. White suspected that widening that transition, making the boundary thicker and the gradient more gradual, might reduce the integrated energy cost substantially. He was right. When White presented his redesigned bubble at the 100-year Starship Symposium in Orlando, Florida, in September 2011, the result he showed had reduced the exotic matter requirement to approximately 700 kilograms. Not 700 kilograms of ordinary matter, 700 kilograms of exotic matter with negative energy density. Still something nobody had ever produced. Still something that might not exist in the required form. But 700 kilograms is the mass of a large motorcycle. It fits in a medium-sized room. It is a number that belongs to the same universe as human engineering, even if it remains far beyond what human engineering can currently produce. White also modified the cross-sectional shape of the bubble from a sphere to a torus, a donut shape, with the spacecraft riding through the central hole. The toroidal geometry concentrated the space-time warping in specific regions and left other areas comparatively flat, reducing the total energy integration across the structure. The combination of thicker boundary and toroidal shape brought the number down by a factor that, stacked on top of Van den Broek's previous reduction, meant the energy requirement had fallen from the mass of the observable universe to the mass of a motorcycle in less than 2 decades of theoretical work. The trajectory was clear. The number was still impossible, but it was moving, and in physics, a number that keeps moving in the right direction is not nothing. White went further still. He proposed that EagleWorks could test whether small-scale space-time warping was detectable in a laboratory setting. The instrument he designed, called the White-Juday Warp Field Interferometer, used a laser beam split into 2 paths and recombined to produce an interference pattern. If space-time curvature existed in one of the paths, even at an extraordinarily tiny scale, the effective length of that path would change slightly, shifting the interference pattern by a measurable amount, The apparatus would surround a high-voltage capacitor arrangement that might, if the theory held at small scales, produce a detectable local distortion of the metric. Eagle Works built the interferometer. They ran the experiments. The results were ambiguous. Signals near the noise threshold of the instrument, possible explanations ranging from actual space-time effects to thermal expansion of optical components to electromagnetic interference from the high-voltage equipment. The controls were not tight enough to permit definitive conclusions. NASA was careful never to claim that warp field effects had been detected, but the fact that NASA had built hardware, run experiments, and published results in peer-reviewed journals was significant in a way that transcended the specific findings. The largest and most credible space agency on Earth had decided that warp drive was worth studying with real instruments in a real laboratory. That decision changed the atmosphere around the field. Graduate students could pursue warp metrics without professional risk. Mainstream journals published the papers. Conferences added sessions on advanced propulsion. The question had moved from, is this worth thinking about, to how do we think about it rigorously? The energy budget had traveled an enormous distance in 17 years. From the mass of the observable universe to 700 kilograms. The geometry had been refined, optimized, reshaped, and tested at the boundary between theory and experiment. The field had developed from a single curious paper into a small but legitimate research program with tools, practitioners, and a shared framework for evaluating new proposals. And yet, at the center of all of it, the same requirement remained: exotic matter, negative energy density, a substance confirmed nowhere in nature at the scales required, whose existence in those quantities remained genuinely uncertain. The question hanging over the entire enterprise was whether that requirement was truly fundamental, written into the physics of warp drive at the deepest level, or whether it was a feature of the specific designs that had been explored so far. Whether the right geometry, the right configuration, the right mathematical insight might someday reveal a warp drive that required no exotic matter at all. The answer came in 2024 from a small private research organization on the 47th floor of an office building in Midtown Manhattan. But before we arrive there, we need to spend a moment with the one confirmed example in all of physics where negative energy has been measured in a laboratory, because it is both the most encouraging and the most humbling data point in this entire story. It proves that what warp drive requires is not absolutely forbidden by nature, and it shows with painful clarity just how far we still have to go. In 1948, a Dutch physicist named Hendrik Casimir was working at the Philips Research Laboratory in Eindhoven, Netherlands. He was 32 years old, methodical, precise, the kind of scientist who preferred to work slowly and get things right, rather than publish quickly and correct errors later. He had been studying the behavior of electromagnetic fields at very small scales, trying to understand how quantum fluctuations in those fields would affect the forces between objects separated by tiny gaps. What he predicted was strange enough that even he was uncertain whether anyone would believe it. Two uncharged, parallel metal plates, placed very close together in a perfect vacuum, Casimir said, should attract each other, not because of gravity, which at those scales is far too weak to measure, not because of static electricity, since both plates carry no net charge. The attraction would come from the quantum vacuum itself, from the structure of empty space, from the fact that emptiness, at the quantum level, is not actually empty at all. To understand what Casimir was predicting, you need to understand what quantum field theory says about the vacuum. In the physics of the very small, the vacuum is not a featureless void. It is a seething medium, constantly alive with activity. Every field that exists in nature, the electromagnetic field, the electron field, the quark fields, all of them fluctuate constantly even in the absence of any real particles. Virtual particles pop into existence in pairs, exist for intervals so brief that no instrument can directly observe them, and annihilate back into nothing. This is not speculation. It is a mathematical consequence of the uncertainty principle, one of the foundational results of quantum mechanics, and it has been confirmed indirectly by measurements of extraordinary precision. These vacuum fluctuations exist everywhere, At all times, in all of space, for all fields, the vacuum is full of them. It hums with energy that no thermometer can measure, and no detector can directly catch, but whose effects are real and observable through their influence on the things we can measure. When you place two metal plates very close together, Casimir realized, you impose a constraint on the electromagnetic fluctuations between them. A metal plate is a boundary condition for the electromagnetic field. Certain wavelengths of electromagnetic fluctuation, the wavelengths longer than the gap between the plates, cannot fit between them. They are excluded from the interior region. But those same wavelengths continue to exist outside the plates, pressing in from both sides. The result is an imbalance. The vacuum outside the plates contains the full spectrum of electromagnetic fluctuations, all wavelengths, all modes. The vacuum between the plates contains only those modes whose wavelengths fit within the gap. The outside is richer, in a precise quantum mechanical sense, than the inside. And that difference in richness produces a net force pushing the plates toward each other. This is the Casimir effect. And the region between the plates, because it contains fewer vacuum modes than the surrounding space, has a lower energy density than the ordinary vacuum outside, lower than empty space, which means, by the definition physicists use, that it has negative energy density relative to the baseline of the vacuum. Casimir published his prediction in 1948. The experimental community took decades to catch up, because measuring a force this small between surfaces this close required instruments that simply did not exist yet. The gap between the plates needs to be on the order of a micrometer, 1/1000th of a millimeter, for the effect to be detectable. At that scale, surfaces are not smooth. They have roughness, vibration, contamination from dust and moisture, all of which produce forces that can obscure the signal. Controlling all of those variables precisely enough to isolate the Casimir force from the noise was an engineering challenge that took 50 years to solve. In 1997, a physicist named Steve Lamoureux at Los Alamos National Laboratory measured the Casimir force for the first time with sufficient precision to confirm Casimir's prediction quantitatively. He used a torsional balance, an extremely sensitive instrument that measured the deflection caused by the force between a metal plate and a metal sphere. His results matched the theoretical prediction to within 15%. Subsequent experiments refined this further. By the early 2000s, measurements in multiple laboratories around the world had confirmed the Casimir effect to within a few percent of the theoretical prediction. The Casimir effect is real. It has been measured, it is reproducible, and the negative energy density it produces in the gap between the plates is genuine, persistent, and physical, not a mathematical artifact or a theoretical abstraction. For the first time in the history of physics, negative energy had been directly confirmed to exist in a laboratory setting. For warp drive researchers, the Casimir effect represented two things simultaneously: the most encouraging result in the history of the field and the most sobering calculation they would ever have to face. Encouraging because it proved the concept. Exotic matter, matter with negative energy density, was not a fantasy invented to make the mathematics work. It existed in nature. You could create it in a laboratory with metal plates and a vacuum chamber. The universe permitted it. The physics allowed it. Every paper that cited the Casimir effect as a proof of principle for warp drive was correct in the narrow sense that mattered most. The substance required was not forbidden. Sobering because of the numbers. A pair of Casimir plates 1 square meter in area, separated by a gap of 1 micrometer, produces a total negative energy in the intervening space of approximately 10 to the negative 7th joules, 1/10 millionth of a joule. To put that in a frame of reference your body understands. The energy required to lift a single grain of rice 1 centimeter off a table is roughly 10 to the negative 5th joules, about 100 times more energy than the entire Casimir cavity contains. The negative energy between those square meter plates is less than the kinetic energy of a mosquito in flight. Harold White's optimized warp bubble design, the most energy-efficient configuration anyone had published at that point, required 700 kilograms of exotic matter. Using Einstein's equation relating mass to energy, 700 kilograms of mass equivalent corresponds to roughly 6 times 10 to the 19th joules of energy. That is 60 billion joules. The Casimir cavity produces 10 to the -7th joules. The ratio between what the warp drive needs and what the Casimir effect produces is approximately 10 to the 26th, a factor of 100 trillion. If you built Casimir cavities covering every square meter of the Earth's surface, stacked them to the height of the atmosphere, and somehow added their contributions perfectly without any interference between them, you would still fall short of the warp drive requirement by many orders of magnitude. The gap was not merely large, it was of a scale that placed the problem in a different category from any engineering challenge humanity had previously attempted. The distance from the Casimir effect to a functional warp drive was not like the distance from a campfire to a nuclear reactor, a large but bridgeable gap in energy scale. It was more like the distance from a single candle flame to the total energy output of the sun, except the ratio was even more extreme. And this was not the only constraint. In the 1990s, physicists Larry Ford and Thomas Roman proved a series of mathematical theorems now known as the quantum inequalities. These theorems showed that negative energy, wherever it appears in quantum field theory, is subject to strict limitations on how much can exist, for how long, and over what volume. The relationship is precise and unforgiving. The more intense the negative energy, the shorter the duration it can persist, and the smaller the region it can occupy. To sustain a large quantity of negative energy over a macroscopic volume for a macroscopic time, as a warp drive would require, was not merely difficult under these theorems. It appeared to approach impossibility in a rigorous mathematical sense. Ford and Roman were careful not to claim an absolute proof that warp drives were impossible. The quantum inequalities applied to the specific framework of quantum field theory in flat spacetime, and corrections from curved spacetime or from physics beyond the standard model might modify them. But within the framework that had been tested and confirmed by decades of experiment, the constraints were severe. The negative energy required for a warp bubble seemed to be precisely the kind of negative energy that the quantum inequalities made most difficult to produce. Researchers proposed various approaches, stacking many Casimir cavities, hoping their contributions would accumulate, using oscillating boundaries to amplify the effect through the dynamic Casimir process, exploring other quantum fields beyond electromagnetism that might produce stronger negative energy under boundary conditions. Each approach ran into the same fundamental obstacle. The gains were real, but tiny. The interference between neighboring cavities prevented linear scaling. The dynamic effects produced even smaller energy densities than the static ones. The other fields produced results that were numerically comparable to the electromagnetic case, but no larger. By the early 2010s, the field had reached what felt like a natural resting point. The warp bubble geometry had been refined. The energy requirement had been driven down from universe scale to motorcycle scale through a series of clever geometric optimizations. The Casimir effect had been confirmed as a real physical phenomenon. The quantum inequalities had been mapped and their implications understood. The situation was as clear as it had ever been, and it presented a picture that was simultaneously more hopeful and more sobering than the original 1994 paper. Warp drive was theoretically valid. Negative energy existed in nature. The energy requirements, while still impossibly large, were finite and had been declining steadily. But the path from where the field stood to an actual functioning bubble was not visible. There was no clear next step, no obvious optimization that would close the remaining gap. The progress that had been made was real, but the distance still to travel was vast, and nobody had a map. What the field needed was not another incremental reduction in the exotic matter requirement. What it needed was a different way of thinking about the problem entirely. That different way of thinking arrived in February 2021 from an unlikely address. 477 Madison Avenue is an office building in Midtown Manhattan, 47 floors of glass and steel, occupying a block in one of the densest urban environments on Earth. It is surrounded by law firms and financial institutions and the headquarters of media companies. It is not the kind of address you would associate with theoretical physics research. It does not have a particle accelerator in the basement or a dome observatory on the roof. Inside that building, on one of the upper floors, is the headquarters of a research organization called Applied Physics. Applied Physics is not a university department. It is not a government laboratory. It is a privately funded research institution supported by investors who had decided that certain fundamental physics problems were worth pursuing systematically, with real resources and real people outside the traditional academic structure. The organization was founded by Gianni Martire, an engineer and entrepreneur who had spent years in aerospace and technology before concluding that the problems he found most interesting were not being attacked aggressively enough by existing institutions. The scientific staff is small, under a dozen core researchers, but they hold advanced degrees from respected universities, publish in peer-reviewed journals, attend international conferences, and engage with the broader physics community as full participants, rather than fringe observers. The Advanced Propulsion Physics Laboratory within Applied Physics was built with a specific mandate: treat warp drive as an engineering problem, not a curiosity, not a thought experiment. A problem with a solution space that could be systematically mapped, explored, and eventually solved. In February 2021, two members of that team, Alexei Bobrik and Gianni Martire, published a paper in Classical and Quantum Gravity. The paper's title was Introducing Physical Warp Drives, and what it introduced was not a new warp drive design. It was something more fundamental than that. It was a framework, a way of classifying every warp drive that had ever been proposed, or could ever be proposed, within a single coherent structure. The core insight was elegant in the way that the best theoretical physics always is. Elegant not because it was complicated, but because it was simple in a way that clarified things that had been obscure. Bobrik and Martire demonstrated that every warp drive spacetime, without exception, regardless of its specific geometry or energy content, consists of three distinct regions. First, an asymptotically flat region far from the ship. This is ordinary space, the kind that fills the universe at large distances from any massive object. Flat, featureless, behaving exactly as Einstein's equations describe for the vacuum. Second, a passenger region at the center. This is also flat. This is where the crew lives, where the spacecraft's hull and systems reside, where clocks tick at normal rates and the laws of physics operate without any unusual effects. The interior of every warp bubble, regardless of how exotic the surrounding geometry might be, is a region of ordinary spacetime. Third, a warping region in between, the shell, the boundary where the metric transitions from flat interior to flat exterior. This is where all the work happens. This is where the space-time compression and expansion occur, where the matter and energy responsible for the warp effect must be concentrated, where the exotic requirements, if any, must be satisfied. Every warp drive ever proposed maps onto this structure. Alcubierre's original bubble, Van den Broek's shrunken exterior design, White's toroidal NASA configuration, Nataru's tangential flow variant. All of them are specific choices of how to fill that middle region, that warping shell, with matter and energy arranged in particular configurations to produce particular geometric effects. The differences between designs are entirely in the warping region. The passenger region and the distant flat exterior are always the same. By establishing this universal structure, Bobrik and Martire could ask systematic questions about the entire solution space rather than about individual designs. Which parts of that space had been explored? Which parts had not? What constraints applied to every possible design? And which constraints were specific to particular geometric choices? One of their most important findings concerned a territory that had been almost entirely ignored: subluminal warp drives. For nearly 3 decades, warp drive research had focused overwhelmingly on superluminal configurations, bubbles moving faster than light, because that was the original motivation. Alcubierre had been thinking about star travel. Star travel requires crossing light years. Crossing light years in reasonable time requires moving faster than light. Every optimization, every refinement, every new design had been aimed at building something that could break the light barrier. Bobrik and Martire pointed out that this focus had caused researchers to overlook a large and potentially more tractable territory: A warp bubble moving slower than light, still using the same three-region structure, still carrying its passengers in a region of flat space-time, still providing the experience of zero acceleration, regardless of how rapidly the bubble itself was changing velocity, might satisfy energy conditions that superluminal designs violated. It might require no exotic matter at all. It might be buildable, in principle, from ordinary matter, following ordinary physics, and it would still be useful, extraordinarily useful. A warp bubble moving at 90% of the speed of light would reach Proxima Centauri in approximately 5 years as measured by external observers. For the crew, due to time dilation, the subjective experience would be shorter. The round trip would fit within a career. Within the solar system, a subluminal warp drive would be transformative on a scale that is difficult to overstate. Mars in days, rather than months. Jupiter in weeks. The outer solar system accessible for the first time to short-duration crewed missions. The paper also proved a theorem that clarified something fundamental about what warp drive actually is. A warp bubble, Bobrick and Martyr showed, is effectively a shell of matter set in motion. The shell moves through space like any other object, subject to the same conservation laws. It requires propulsion to accelerate it to its cruising velocity. Warp drive does not eliminate rockets. It changes what the rocket is pushing. Instead of pushing the spacecraft directly, transmitting forces to the hull and through the hull to the crew, the propulsion system accelerates the bubble. The bubble carries the interior region with it, but transmits no forces across the flat space-time of the passenger region. The crew feels nothing. The ship experiences no structural stress. The bubble moves and everything inside it moves with it, but nothing inside it is being pushed. This was a conceptual clarification of genuine importance. Warp drive had sometimes been described as if it were magic, as if it somehow bypassed the need for propulsion entirely. Bobrick and Martyr showed that it did not. It was a structured space-time geometry that, once built and set in motion, carried its contents without accelerating them directly. The fuel and the engines were still necessary. They were just doing a different job. The 2021 paper became the standard reference for the field almost immediately. Every subsequent paper on warp drive cited it. The three-region classification scheme became the shared vocabulary. The focus on subluminal configurations opened a research direction that attracted new attention, and applied physics, having established the framework, turned to the problem of finding a specific solution within it. A design that satisfied all the physical requirements, used no exotic matter, and demonstrated that the subluminal territory Bobrick and Martyr had identified was not merely theoretically available, but actually occupiable. They found it 3 years later. Classical and Quantum Gravity, Volume 41, Number 9, Article 095013, published April 29, 2024. The title was Constant Velocity Physical Warp Drive Solution. Lead author, Jared Fuchs. Co-authors Christopher Helmerich, Alexei Bobrick, Luke Sellers, Brandon Melcher, Gianni Martyr. The entire applied physics team working together, focused on a single problem for the better part of 3 years, and arriving at a result that no one in the field had achieved in the 30 years since Alcubierre's original paper. What the paper claimed was this: a warp drive spacetime that satisfies all of the classical energy conditions, every one of them. The energy conditions are mathematical criteria that ordinary matter satisfies and exotic matter violates. They are not arbitrary rules invented to make life difficult for warp drive researchers. They emerge from quantum field theory and from the requirement that physics behave causally, that information not travel backward in time, that matter not spontaneously generate itself from nothing. They have been confirmed by every experiment ever conducted. Violating them means proposing matter or energy that has never been observed and that current physics provides no mechanism to produce. The weak energy condition says that no observer should ever measure a negative energy density at their location. The null energy condition says that light rays should not experience negative energy as they propagate. The dominant energy condition says that energy should not flow faster than light. The strong energy condition is a constraint related to how gravity behaves in the presence of matter. Every warp drive proposed before the Fuchs paper violated at least one of these conditions. Every single one. The exotic matter requirement that had plagued warp drive research from the beginning was precisely the requirement to violate the energy conditions to fill some region of the warping shell with matter that had never been observed and might not exist. The Fuchs warp drive violates none of them. No negative energy anywhere in the structure, no exotic matter, no requirement for any substance or phenomenon that has not been confirmed to exist in the physical universe. The design combines two elements working in concert. The first is a matter shell, a distribution of ordinary positive energy material arranged in a specific geometry around the passenger region, not exotic matter. Ordinary baryonic matter, the protons and neutrons and electrons that make up everything visible in the universe, distributed according to a precise density profile that the mathematics specifies. The second element is what physicists call a shift vector distribution, a feature of the space-time metric that describes how different parts of space are moving relative to each other. In the Fuchs design, the shift vector creates a flow pattern that mimics the Alcubierre geometry in its essential character. Space is slightly compressed ahead of the bubble, slightly expanded behind it. The bubble translates forward, the passenger region moves with it, but the compression and expansion are driven by the ordinary matter shell, interacting with the shift vector structure, not by exotic matter with negative energy density. The same geometry that Alcubierre described, the same three-region structure that Bobrick and Martier classified, achieved using only the materials that the universe actually provides. The applied physics team evaluated their design using a software tool they had developed and released publicly called Warp Factory, written in MATLAB and available to any researcher who wanted to use it. Warp Factory accepts any proposed warp metric as input and calculates its properties. The stress energy tensor, which tells you what kind of matter would be needed to produce that geometry. The energy conditions, which tell you whether that matter is physical. The curvature scalars, which describe how strongly space-time is bending, and visualizations that allow researchers to inspect the geometry directly. When you input the Fuchs metric into Warp Factory and run the calculation, the output shows blue everywhere. Blue indicates positive energy density, ordinary matter, the kind that satisfies all the energy conditions. Nowhere in the visualization does red appear. Red would indicate an energy condition violation, a region requiring exotic matter. The Fuchs warp drive has no red regions. It is entirely blue, entirely physical, entirely consistent with everything physics has confirmed about the real universe. Fuchs described the result plainly in interviews following publication. Prior warp drive models required matter and energy content that was unphysical, he said, features nobody has ever observed in nature. The new approach avoided that by using only positive energy, phenomena like ordinary matter and light, all of which exist naturally, all of which we can detect and measure, and in some cases produce at will. The solution also uses gravity itself as part of the warping mechanism, which in retrospect feels almost obvious. Gravity is the manifestation of curved spacetime, a sufficiently dense and precisely shaped distribution of ordinary matter curves the space around it. That curvature, combined with the shift vector structure, produces the warp effect without requiring anything the universe refuses to provide. The mechanism has been operating since the first stars formed, producing space-time curvature around every massive object that has ever existed. The Fuchs paper shows how to arrange that curvature deliberately in the specific configuration a warp bubble requires. For the first time in 3 decades of warp drive research, a design existed that connected to the physical universe. The physics community responded with the kind of cautious, precise optimism that characterizes serious science. The solution was mathematically valid. The energy conditions were satisfied as claimed. The result had been reviewed by experts who found no errors in the analysis. The paper was a genuine advance. Mainstream physicists who had previously found reasons to dismiss warp drive research began citing the Fuchs paper in their own work. The caveat that headlines consistently buried was this: the Fuchs warp drive is explicitly subliminal. The bubble moves at a constant velocity less than the speed of light. It does not enable travel to Proxima Centauri in days or weeks. It does not break Einstein's cosmic speed limit. Fuchs was unambiguous about this in every public statement. This concept, he said, will not deliver Star Trek-style interstellar transport. What it delivers is the warp effect itself, demonstrated using only ordinary matter and ordinary physics. The ability to move a region of flat spacetime through the universe without transmitting any acceleration forces to the interior. That capability, even at subluminal speeds, changes what is physically possible in ways that no previous propulsion concept has achieved. Consider what subliminal warp actually means for human activity in the solar system. A warp bubble accelerating continuously at rates that would crush an unprotected crew delivers those forces entirely to the bubble's shell, not to the passenger region. The crew inside feels nothing. They could be reading, sleeping, working, while the bubble outside accelerates at hundreds of times the force of gravity. A ship that can accelerate hard, coast briefly, and decelerate hard, without any of those forces reaching the people inside, transforms the geometry of human activity within the solar system so completely that the comparison to current capabilities almost ceases to be meaningful. Mars in days, Jupiter in weeks, the moons of Saturn within reach of missions measured in months rather than years, the Kuiper Belt accessible for the first time, the heliopause, where our sun's influence gives way to the interstellar medium, reachable within a career. The entire solar system, which currently feels vast and largely inaccessible beyond the inner planets, becomes a neighborhood. And beyond the solar system, a subliminal warp bubble at 90% of light speed reaches Proxima Centauri in about 5 years. The crew's subjective experience, compressed by time dilation, would be shorter. A round trip would be long. It would require commitment, but it would be within the span of a single human life. Someone could volunteer for the mission, make the journey, and return. Not a generation ship, not a one-way voyage into permanent exile. A mission with a departure date and a return date, both within the working years of the crew members who signed on. The engineering challenges between this result and that future are, to be clear, immense. The matter shell that the Fuchs design requires must maintain a density profile specified to extraordinary precision under gravitational stresses, thermal fluctuations, and the dynamic forces of acceleration and deceleration. The materials needed to sustain that configuration under those conditions do not exist. Current high-strength materials, advanced steel alloys, carbon fiber composites, can handle pressures up to a few gigapascals. The warp shell would need to handle stresses orders of magnitude higher without deforming. We are not decades away from that capability. We are likely centuries away. The energy required to accelerate even a subliminal warp bubble to a significant fraction of light speed is enormous. Not exotic, not impossible in principle, but large in ways that challenge current global energy infrastructure even to contemplate sustained terawatt-scale power over the hours or days of an acceleration phase. We have never attempted anything close to that. The instrumentation needed to test even laboratory-scale warp effects at the precision the theory requires does not yet exist. Before anyone builds a warp ship, someone must demonstrate the effect at bench scale. Detect the space-time curvature produced by a small matter distribution configured according to the Fuchs geometry. Current instruments can detect gravitational waves from black holes merging billions of light years away. But that is a dynamic signal, a ripple propagating across the universe. Measuring a static local curvature from a small engineered mass distribution is a fundamentally different problem, one that requires a different class of instrument that has not yet been built. Nobody is constructing a warp drive this decade, almost certainly not this century. The gap between the 2024 paper and a functioning vehicle is not a gap that optimism or funding can close in any near-term timeframe. It is a gap measured in centuries of materials, science, energy technology, and precision instrumentation, all of which must advance dramatically before the first test bubble can be assembled. But the physics permits it. That is what changed on April 29, 2024. Not the timeline, not the engineering feasibility, the physics. For the first time, a warp drive design existed that required nothing the universe refuses to provide. That is not a small thing. That is the difference between a door that is locked and a door that is open, even if the hallway beyond it is very, very long. There is a version of this story that ends with the 2024 paper and feels complete. A warp drive that works, a design built from ordinary matter. A future where the solar system opens up and the stars begin, slowly, to feel less permanent in their distance. That version is real, the physics is genuine, the result stands, but it is only part of the story. Because the question that drove warp drive research from the beginning was never really about Mars in days or Jupiter in weeks. It was about the stars, about Proxima Centauri, about Sirius and Vega, and the hundreds of billions of other suns scattered across the galaxy, each one potentially orbited by worlds, some of them potentially harboring something we have not yet found anywhere else in the universe. The subliminal warp drive is a profound achievement. It is not the answer to that question. The answer to that question requires crossing 4 light years in years, not decades. It requires superluminal travel, faster than light. And when you push the warp bubble past that threshold, past the speed of light itself, the physics does something that no engineering can fix, no geometric optimization can avoid, and no amount of exotic matter can resolve. It creates a horizon. To understand what a horizon means for a warp bubble, you need to understand what a horizon means at all. The most familiar example is a black hole. At the event horizon of a black hole, space-time is falling inward faster than light can propagate outward. A photon trying to escape from just inside the horizon finds that the space ahead of it is receding faster than it can travel. It swims against a current stronger than itself. It never makes progress. From the outside, nothing crosses that boundary outward. Not light, not information, not any signal of any kind. The horizon is a one-way membrane in the fabric of space-time, permeable in one direction only. Now consider a warp bubble moving faster than light. The front wall of the bubble is advancing through space at a superluminal velocity. A signal generated inside the bubble, moving at the speed of light toward the front wall, cannot catch up. The wall is receding faster than the signal can travel. The front edge of the bubble is, from the perspective of the interior, unreachable. No information sent from the pilot's seat can ever arrive at the leading edge of the bubble. No command, no course correction, no emergency signal. The front wall of the bubble is as causally disconnected from the crew as the interior of a black hole is from the universe outside. This is the horizon problem, and its consequences are immediate and severe. During a superluminal warp voyage, the crew cannot steer, not in the sense that steering is difficult or requires special equipment, in the sense that the causal structure of space-time makes it physically impossible. A course correction requires sending a signal to the part of the bubble that needs to change its geometry, the leading edge. That signal cannot arrive. The front wall does not receive it. The geometry does not change. The bubble continues on whatever vector it was set to at the moment it crossed the light barrier, with perfect indifference to anything the crew might subsequently discover about obstacles, errors in navigation, or changed destinations. Before departure, the trajectory must be correct, precisely correct, because once the bubble is moving faster than light, there is no correcting it. It gets worse. To decelerate, to bring the bubble back below light speed and eventually to rest at the destination, the bubble's geometry must change. The compression in front and the expansion behind must be gradually reduced, the metric relaxing back toward flat spacetime as the bubble slows. But changing the bubble's geometry requires sending signals from the ship's interior to the bubble boundary. At superluminal speeds, those signals cannot reach the leading edge. The crew cannot decelerate the bubble from inside it. They have no causal access to the mechanism that would bring them to a stop. The only ways to stop a superluminal warp bubble are to have pre-positioned infrastructure at the destination, equipment set up by an earlier mission or an already present civilization that can collapse the bubble from outside, or to have autonomous systems built into the bubble wall itself, pre-programmed to shut down after a specific duration or upon detecting specific conditions. Neither option is reassuring. The pilot of a superluminal warp ship is not a pilot in any meaningful sense. They are cargo. The ship is a ballistic device that was aimed before launch and will arrive where it was pointed, on the schedule determined before departure, regardless of anything that happens in between. Some theorists have proposed oscillating the bubble, switching it on and off at high frequency to preserve brief windows of causal contact with the outside universe between pulses. The mathematics for this exists in certain formulations, but the instabilities introduced by a bubble that repeatedly collapses and reforms are severe. Each cycle of collapse and reformation releases energy. The radiation emitted with each pulse could be enough to sterilize the interior. A crew surviving the horizon problem by riding an oscillating bubble might survive the navigation issue only to be killed by the solution. The horizon problem is a navigation catastrophe. What comes next is worse. It is a survival problem. In 1974, Stephen Hawking published a result that fundamentally altered the physics community's understanding of black holes and, by extension, of horizons everywhere. Before Hawking's work, black holes were understood to be perfectly black in a literal sense. They absorbed everything and emitted nothing. No light, no heat, no radiation of any kind escaped them. They were cold, silent, dark. Hawking showed that this picture was wrong. Near the event horizon of a black hole, the quantum vacuum behaves in a specific and consequential way. Virtual particle pairs constantly appear from the vacuum, as they do everywhere in space at all times. Normally, these pairs annihilate almost immediately, returning their borrowed energy to the vacuum and vanishing. But near a horizon, something different can happen. One particle of a pair can fall inward across the horizon while the other escapes outward. The infalling particle carries negative energy into the black hole, slightly reducing its mass. The escaping particle becomes a real photon, carrying positive energy away from the black hole into the surrounding universe. From the perspective of a distant observer, the black hole appears to be radiating, emitting a thermal spectrum of photons with a temperature that depends on the black hole's mass. Large black holes are cold. A black hole with the mass of our Sun would have a Hawking temperature of about 60 nanokelvin, 60 billionths of a degree above absolute zero, unmeasurably cold against the background of the cosmic microwave radiation, but the temperature scales inversely with mass. Smaller black holes are hotter. A black hole the mass of a mountain would radiate at temperatures detectable by instruments. A microscopic black hole would be extraordinarily hot. The horizon of a superluminal warp bubble is not identical to a black hole event horizon, but it shares the relevant structural feature. It is a boundary in spacetime where causal structure changes, where future directed paths cannot cross in one direction. And wherever that structure exists, quantum field theory predicts that Hawking-like radiation should appear. Near the front wall of a superluminal warp bubble, virtual particle pairs appear from the vacuum. One particle falls forward into the region of space the bubble is moving into. The other falls backward into the interior of the bubble, where the crew is located. From the crew's perspective, particles are continuously arriving from the direction of the front wall, a steady stream of radiation, generated not by any external source but by the horizon geometry of the bubble itself, pouring inward. The temperature of this radiation depends on the size of the horizon, which for a warp bubble is related to the size of the bubble itself. Warp bubbles are small, much smaller than astrophysical black holes, and because temperature scales inversely with horizon size, a warp bubble's Hawking radiation would be far hotter than anything a stellar mass black hole produces. A paper published in 2009 by physicists at the University of Sydney worked through this calculation in careful detail. Their conclusion was stark. A macroscopic superluminal warp bubble, moving at 10 times the speed of light, would generate Hawking radiation at its leading edge, with an effective temperature of thousands to millions of Kelvin. The radiation would consist of high-energy photons, X-rays, gamma rays, and potentially more energetic particles, streaming continuously into the interior of the bubble from the front wall. The intensity would be lethal to any biological organism within seconds of the bubble crossing the light barrier. The faster the bubble moved, the hotter the radiation. There was no threshold at which superluminal travel became safe. The radiation was a direct consequence of the horizon, and the horizon was a direct consequence of the superluminal velocity. No shielding addresses this problem. The radiation is not arriving from outside the bubble. It is being generated inside the bubble, between the ship and the front wall, by the quantum vacuum responding to the local horizon geometry. Putting absorbing material between the crew and the front wall would require disrupting the bubble geometry in exactly the region where the warping must be most precise. Any disruption of that region collapses the drive. The crew cannot hide from the radiation without destroying the ship. Some researchers have speculated that quantum gravity corrections might modify Hawking radiation at the scales relevant to a warp bubble. Quantum gravity is the still undiscovered theory that would unify general relativity with quantum mechanics, describing the behavior of spacetime at the Planck scale, roughly 10 to the negative 35 meters, where both theories become simultaneously relevant. At those scales, spacetime itself might behave in ways that alter how horizons emit radiation. The modification might reduce the intensity, it might eliminate it entirely, or it might make it worse. We do not know. We do not have a theory of quantum gravity. It is the most sought-after result in theoretical physics, the problem that occupied Einstein for the last 3 decades of his life without resolution, the challenge that string theory, loop quantum gravity, and dozens of other research programs have been attacking for 50 years without producing a confirmed result. Until that theory exists and has been tested, any speculation about how it might affect Hawking radiation in a warp bubble is exactly that, speculation. What is not speculation is the subluminal escape clause. A warp bubble moving slower than light does not cross the threshold where a true horizon forms. Without a horizon, quantum field theory predicts no Hawking radiation. The crew is safe from this particular hazard. The physics permits subluminal warp without irradiating the passengers. It is yet another way in which the Fuchs result, confined to subluminal speeds, avoids problems that superluminal travel makes inescapable. The horizon problem removes the ability to navigate. The Hawking radiation problem removes the ability to survive. The third problem with superluminal warp travel removes the ability to arrive without causing catastrophe. Interstellar space is not empty. This is worth stating clearly because the word vacuum suggests a completeness of nothingness that does not accurately describe the interstellar medium. The space between stars contains approximately 1 hydrogen atom per cubic centimeter on average. Occasional helium atoms, trace amounts of heavier elements, microscopic dust grains, free electrons and ions, cosmic ray particles traveling at high velocities. The density is extraordinarily low by any terrestrial standard. For a spacecraft moving at conventional speeds, this thin medium presents no obstacle. Voyager 1 has been traveling through it for nearly 50 years without any measurable effect on its trajectory or structure. But a warp bubble moving at superluminal velocities interacts with this thin medium in a way that conventional spacecraft do not. The interaction was worked out in a 2012 paper by Brendan McMonigal, Geraint Lewis, and Philip O'Byrne at the University of Sydney. The question they asked was simple. What happens to the hydrogen atoms and dust grains in the path of a superluminal warp bubble? The answer was alarming in a way that reframed the entire prospect of superluminal warp travel. As the bubble advances through the interstellar medium, the particles in its path do not pass cleanly through the bubble boundary. They are caught. The compressed spacetime geometry at the leading edge acts as a trap. Particles that encounter the front wall of the bubble are swept up by the warped geometry and accelerated to enormous energies as the compression acts on them. They accumulate in the region just ahead of the inner boundary of the passenger region, building up continuously throughout the voyage, each new particle adding to the reservoir that the previous particles began. The longer the voyage, the greater the accumulation. A journey of 1 light-year sweeps up every particle in a cylinder of interstellar medium, 1 light-year long and as wide as the bubble's cross-section. A journey of 4 light-years to Proxima Centauri sweeps up 4 times as much. The particles arrive with energies proportional to the bubble's velocity. At 10 times the speed of light, each captured particle carries 10 times the energy it would at light speed. The reservoir grows in energy with both distance and velocity. When the bubble finally arrives at its destination and the drive is shut down, the geometry relaxes. The compressed space-time releases its grip on the accumulated particles. Everything that was trapped throughout the voyage is suddenly free, and it moves in the direction the bubble was traveling, directly toward the destination, in a tightly focused beam of high-energy particles. McMonagall, Lewis, and O'Byrne calculated the energy content of this beam for a voyage to Proxima Centauri. The numbers were devastating. The beam would carry energy equivalent to the detonation of thousands of nuclear weapons, concentrated into a narrow cone aimed directly at the destination star system. Any planet in the path would have its atmosphere stripped away. Its surface would be irradiated beyond any possibility of supporting life. If the beam was intense enough and the planet small enough, the surface material itself might be vaporized. A warp ship arriving at Proxima Centauri would not land gracefully. It would sterilize the system. The crew inside the bubble would survive. They were shielded by the bubble geometry throughout the voyage and are now at rest in flat space-time as the beam disperses ahead of them. But the civilization that sent them would have just committed an act of interstellar destruction even without intending to. Even if Proxima Centauri b, the potentially habitable planet confirmed to orbit within that star's habitable zone, harbored no life at all, the beam would remove any possibility of it ever doing so in the future. And if something did live there, it would be gone. This is sometimes called the warp drive particle beam problem, and unlike the horizon problem or the Hawking radiation problem, it does not arise from exotic quantum physics or the behavior of space-time at extreme scales. It arises from the basic mechanics of a bubble moving through a medium that contains particles. It would occur at any superluminal speed for any bubble geometry, regardless of how cleverly the design was optimized in other respects. The interstellar medium is there. The bubble traps particles. The particles accumulate. The arrival releases them. The physics is straightforward, and the conclusion is unavoidable. Proposed solutions exist, but none of them is clean. One approach involves shaping the bubble's leading edge hydrodynamically, designing the front wall to deflect incoming particles around the sides of the bubble rather than trapping them. The geometry would need to act like the prow of a ship, guiding the medium around the obstacle rather than compressing it into a reservoir. Whether this is achievable while maintaining the geometric conditions necessary for warp function is an open question. Every modification to the bubble boundary affects the metric, which affects the warp effect, which affects the entire purpose of the structure. Another approach involves terminating the voyage far from the destination, in the emptiness between star systems, and allowing the particle beam to disperse before approaching the target under conventional propulsion. The beam expands as it travels. Given sufficient distance, its energy density at the target might drop below the threshold for catastrophic damage. But this requires knowing in advance where to stop, having conventional propulsion capable of completing the final approach, and accepting that the warp drive cannot be used for the final phase of the journey. It transforms the warp ship from a point-to-point vehicle into a two-stage system with all the complexity that entails. A third approach simply accepts the limitation and designs interstellar missions around it. Warp drives become long-range ballistic delivery systems. They are aimed away from inhabited regions or toward destinations confirmed to be lifeless, and the particle beam problem is managed by careful selection of trajectories and terminal points. This might be workable in a universe where humanity has already mapped its destinations thoroughly. It is useless for exploration, where the point is to discover what is at the destination before arriving. Between the horizon problem, the Hawking radiation problem, and the particle accumulation problem, the superluminal warp drive begins to look less like a starship and more like an uncontrollable weapon that happens to transport passengers. The original vision, a crude vessel that a pilot could navigate between star systems on demand, departing when ready, steering en route, arriving safely, exploring freely, is not what the physics actually produces when you push the bubble past the speed of light. What the physics produces is something more like a guided missile, requiring external stopping infrastructure, incapable of course correction, lethally radioactive to its crew if the quantum calculations are correct, and devastating to whatever it encounters at arrival. That is not the vehicle that makes humanity a spacefaring civilization in any meaningful sense. Which raises the question that has always lurked at the edge of this discussion. If warp drive comes with all of these problems in its superluminal form, is there a different approach entirely? A way of reaching the stars that does not require warping space around a bubble and racing through the interstellar medium at velocities that trap particles and create horizons? There is. In a sense, instead of moving a bubble of space-time from one star to another, imagine connecting 2 points in space-time directly, not moving through the space between them, but eliminating the need to cross that distance at all. A tunnel, a shortcut, an opening in the fabric of space-time that leads from one location to another, through a path shorter than the surrounding universe. You step through one end, and you emerge from the other, light years away moments later. This is a wormhole, and like warp drive, it emerges from Einstein's equations as a mathematically valid solution. The mathematics of wormholes begins in 1935, when Albert Einstein and his colleague Nathan Rosen were studying the interior structure of black holes using the Schwarzschild metric, the simplest solution to Einstein's field equations describing the spacetime around a spherically symmetric mass. While examining the geometry carefully, they noticed something unexpected. The mathematics permitted a bridge, a geometric connection between two otherwise separate regions of spacetime, one on each side of the singularity at the center. The Einstein-Rosen bridge, as it came to be known, was a feature of the mathematics rather than something anyone expected to find in nature. It was not traversable. The bridge existed only for an infinitesimal moment before collapsing under gravitational pressure, far too briefly for anything to pass through. Anyone attempting to enter it from either end would be crushed before reaching the other side. As a practical means of travel, the Einstein-Rosen bridge was useless. The situation changed in 1988. Kip Thorne was a theoretical physicist at Caltech, one of the most respected figures in general relativity, who would later share the 2017 Nobel Prize in Physics for the first detection of gravitational waves. Thorne had a reputation for taking unconventional questions seriously, for being willing to follow the mathematics wherever it led, even when the destination seemed outlandish. Carl Sagan, writing his novel Contact, asked Thorne whether general relativity permitted any form of faster-than-light travel that a novelist could use without embarrassing himself scientifically. Thorne took the question to his graduate students. The result, published in 1988 with co-authors Michael Morris and Ulvi Yurtseva, was striking. Traversable wormholes were valid solutions to Einstein's equations, not the collapsing bridges of the 1935 result. Stable, open, passable tunnels connecting two mouths separated by any distance in space or time. A spacecraft could enter one mouth, travel through the throat connecting the mouths, and emerge from the exit potentially light years away. The journey through the throat might take minutes or hours. The two mouths could be anywhere in the universe. Think of space-time as a sheet of paper. To travel from one point to another across its surface, you follow the route across the sheet, the long way around. A wormhole is like folding the paper, so the 2 points touch, then poking a hole through both layers. The hole connects them. The distance through the hole is negligible compared to the distance across the surface. The ship does not travel faster than light through the throat. Locally, inside the tunnel, light still moves at its standard speed and nothing exceeds it. But the shortcut makes the effective travel time between origin and destination far less than light could achieve, following the path through ordinary space. Thorne's paper established the requirements for a traversable wormhole with careful precision. The wormhole must have no event horizon. It must be wide enough for a spacecraft to pass without being destroyed by tidal forces. Its geometry must remain stable against perturbations. And it must be held open. That final requirement is where the wormhole problem converges with the warp drive problem, arriving at the same obstacle from a different direction. Ordinary matter curves spacetime inward. Gravity is attractive. A wormhole throat, a tunnel through spacetime, naturally wants to pinch shut under the attractive force of the matter surrounding it. It is gravitationally unstable. To hold it open, you need something that curves spacetime outward, something that pushes rather than pulls. something with negative energy density, exotic matter. Again, and for a wormhole, the exotic matter is not a shell that might be optimized away through clever geometric choices. It is structural. It is literally holding the throat open against the constant gravitational pressure trying to collapse it. Remove it for any duration, and the throat pinches shut. Whatever is inside the throat at that moment ceases to exist. The exotic matter requirement for a traversable wormhole is not a consequence of a specific design choice. It is a consequence of what a wormhole is. The quantities required are not small. Thorne's original calculations suggested exotic matter comparable to the mass of a large planet would be needed to hold open a throat wide enough for a human-scale spacecraft. More recent analyses have confirmed that the requirement scales with the size of the throat and the length of the tunnel. A wormhole designed to serve as a regular transit point between star systems would require exotic matter measured in stellar masses, all concentrated in the throat geometry with extraordinary precision. Unlike the subliminal warp drive, where the Fuchs paper demonstrated that ordinary matter could produce the warp effect, no analogous result exists for wormholes. Every traversable wormhole solution ever written down requires exotic matter in the throat. The no-go results in this domain are stronger and more general than for warp drive. The mathematical theorems that would need to be circumvented are more fundamental. While subliminal warp has found a path to ordinary physics, wormholes remain entirely dependent on physics we have never observed. For anyone assessing the two approaches honestly, the comparison points clearly in one direction. Warp drive, in its subliminal form, connects to the physical universe. It uses matter that exists. Its energy conditions are satisfied. It has a visible, if distant, engineering path. Wormholes require a fundamental advance in physics, something beyond everything we currently know, before the first traversable example could even be contemplated. Both concepts live in the mathematics of general relativity. Only one of them, so far, has found a foothold in physical reality. The stars are still far away, the barriers are real. 3 of them, for superluminal warp, are potentially insurmountable with any physics currently available. And wormholes, for all their elegance, require a breakthrough we have not made and cannot currently see the path to making. But the story does not end here, because in 2024, the same year the Fuchs paper appeared, a different research group asked a question nobody had thought to ask in 30 years of warp drive physics. Not how to build a warp drive, not how to make one that satisfies the energy conditions, but what happens when one fails. And the answer to that question opened a window onto the cosmos that nobody had anticipated. Every instrument humanity has ever pointed at the sky has been looking for the same thing, in one form or another, a signal, something that does not belong to the natural universe, something shaped by intention, by intelligence, by the deliberate action of minds that evolved somewhere other than Earth and built something we could detect across the distance between stars. For 70 years, that search has focused almost entirely on electromagnetic radiation. Radio telescopes scanning billions of frequencies for a pattern that could not have been produced by a pulsar or a quasar or the thermal noise of interstellar gas. Optical telescopes watching for laser pulses, tight beams of coherent light aimed at our solar system with a precision that nature does not achieve on its own. Infrared surveys searching for the waste heat that a sufficiently advanced civilization would inevitably radiate, the thermodynamic signature of a species that had learned to harvest the energy of its star on an industrial scale. All of these searches rest on the same assumption, that an advanced civilization, wherever it exists, whatever it has built, will leak electromagnetic radiation we can detect. That the universe is, in some sense, transparent to the signals intelligence produces. In 2024, a physicist named Katie Clough and her collaborators at Queen Mary University of London asked a different question, not whether civilizations leak electromagnetic signals, but whether they leak something else entirely, something that travels through the universe by a completely different mechanism, something that no telescope, no radio receiver, no optical interferometer was designed to find. Gravitational waves. Gravitational waves are ripples in the fabric of space-time itself. They are produced whenever massive objects accelerate, and they propagate outward at the speed of light, passing through matter with almost no interaction, crossing the universe unimpeded by the gas clouds and dust that absorb or scatter electromagnetic radiation. A gravitational wave produced in a galaxy a billion light-years away arrives at Earth, carrying information about the event that created it, information that no electromagnetic signal from the same event could deliver, because the event is hidden behind dust, inside a dense stellar environment, or simply too far away for its photons to be distinguishable from the background. The Laser Interferometer Gravitational Wave Observatory, LIGO, detected gravitational waves for the first time on September 14, 2015. The signal lasted less than a second. It was produced by two black holes, each roughly 30 times the mass of our Sun, spiraling together and merging approximately 1.3 billion light-years from Earth. The peak power of the event, in the final fraction of a second before merger, exceeded the combined luminosity of every star in the observable universe, and the distortion it produced in the fabric of space-time when it reached Earth after traveling 1.3 billion light-years was a change in the length of LIGO's 4-kilometer arms of approximately 1,000th of the diameter of a proton. That is what LIGO detected. A change in length smaller than an atomic nucleus, sustained for less than a second, produced by an event a billion light-years away. The instrument is among the most precise measurement devices ever constructed by human beings, and the signal it found was almost incomprehensibly faint. Clough's question was whether that same instrument, or instruments like it built with even greater sensitivity, might be able to detect something no one had previously considered: the gravitational wave signature of a warp drive failing. Music. A warp bubble is a structured region of space-time. It is held in a specific geometric configuration by the matter and energy arranged within its warping shell. Like any physical structure, it is subject to perturbations. Small fluctuations in the matter distribution, tiny variations in the metric components, random quantum effects that push the geometry slightly away from its designed configuration. A sufficiently stable bubble maintains its shape against these perturbations, returning to equilibrium after each small disturbance. The way a well-designed bridge sways in the wind without collapsing, an insufficiently stable bubble does not. The perturbation grows. The geometry departs further and further from the designed configuration, and the bubble collapses. When a warp bubble collapses, the process is not gentle. The curved space-time geometry that was being maintained by the matter shell suddenly relaxes back toward flat. All the energy stored in the curvature, the energy that was producing the compression in front and the expansion behind, is released. The release is rapid, catastrophic, and it propagates outward from the collapse point at the speed of light in the form of gravitational waves. Clough's team used numerical relativity to model this process. Numerical relativity is a branch of computational physics that solves Einstein's field equations on supercomputers by discretizing space-time into a grid and evolving the equations forward in time, step by step, tracking how the geometry changes in response to the matter and energy distribution at each moment. It is the same technique used to simulate black hole mergers, neutron star collisions, and supernova core collapses, the events that LIGO and its sister observatory Virgo were built to detect. The calculations are extraordinarily demanding, requiring thousands of processor cores running in parallel for days or weeks to simulate a single event. Clough's group set up a warp bubble metric in their simulation. They specified a physically reasonable matter distribution within the warping shell. They allowed the simulation to run, tracking the evolution of the geometry over time. Then they introduced a small perturbation, a minor fluctuation in the matter distribution, the kind of thing that might occur in a real bubble due to quantum effects or small engineering imperfections. They watched the bubble collapse, and they recorded the gravitational wave signal that the collapse produced. The waveform had a specific and distinctive shape, an initial burst of high-frequency oscillations as the geometry began to depart from equilibrium, growing in amplitude as the collapse accelerated. A peak as the bubble's structure disintegrated and the stored curvature energy was released in a concentrated pulse. Then a ring down, a decaying sinusoidal pattern as the space-time geometry settled back toward flat, oscillating with decreasing amplitude around its final equilibrium state, the way a struck bell rings with diminishing intensity after the initial blow. The overall shape was recognizable to anyone familiar with gravitational wave astronomy. Ring-downs are a standard feature of many astrophysical events. Merging black holes ring down as the newly formed remnant settles into a stable Kerr geometry. Oscillating neutron stars ring down as their vibrations are damped by gravitational wave emission. But the specific characteristics of the warp bubble collapse signal, its frequency, its duration, its amplitude profile, its spectral content, did not match any of those known sources. It was something new, a gravitational wave waveform that had never been observed, produced by a physical process that had never been considered as a source of gravitational radiation, carrying information about a type of object that had never been detected. The frequency of the signal depended on the size of the warp bubble. For a bubble with a diameter of a few kilometers, consistent with a spacecraft large enough to be useful, the dominant gravitational wave frequency fell in the range of several hundred kilohertz, 300 kilohertz, 300,000 oscillations per second. LIGO operates in the frequency range of roughly 10 Hz to a few kilohertz. Its sensitivity peaks at around 100 Hz. A warp bubble collapse signal at 300 kilohertz would be completely outside LIGO's detection band. Even if a warp bubble collapsed in our own galaxy, in the immediate cosmic neighborhood of our solar system, LIGO would hear nothing. The instrument is simply not tuned to the right frequency range. But LIGO is not the only gravitational wave observatory that exists, or that is being planned. The gravitational wave sky is divided by frequency into bands, the way the electromagnetic sky is divided into radio, infrared, optical, ultraviolet, X-ray, and gamma-ray regimes. LIGO covers the audio frequency band, the range where merging stellar mass black holes and neutron stars produce their loudest signals. The Laser Interferometer Space Antenna, LISA, a planned European Space Agency mission consisting of 3 spacecraft separated by millions of kilometers in a triangular formation, will cover the millihertz band, where supermassive black hole mergers and compact binary systems produce signals too low in frequency for ground-based detectors. Pulsar timing arrays, networks of precisely measured millisecond pulsars distributed across the galaxy, cover the nanohertz band, detecting the gravitational wave background produced by the slow in-spiral of the most massive objects in the universe. None of these covers the kilohertz to megahertz range where warp bubble collapse signals would appear. But proposals exist for high-frequency gravitational wave detectors that would operate in exactly that range. Designs based on superconducting resonators, devices that ring at specific mechanical frequencies and can detect gravitational waves by measuring tiny changes in their oscillation patterns. Designs based on levitated microspheres, microscopic objects held in place by magnetic or optical traps, whose position can be tracked with extraordinary precision, sensitive to gravitational wave strains at high frequencies. Designs based on microwave cavity arrays, arrangements of electromagnetic resonators that respond to the perturbation of space-time geometry passing through them. None of these designs has been built at the scale necessary to detect astrophysical gravitational wave sources. They exist as theoretical proposals and small-scale prototypes. Their sensitivity is still orders of magnitude short of what would be needed to detect a signal from outside the solar system. But the trajectory of gravitational wave astronomy has been consistent since the field began. Each generation of instruments is more sensitive than the last. LIGO itself was upgraded from its initial configuration to advanced LIGO, gaining a factor of 10 in sensitivity and opening the universe of astrophysical sources that initial LIGO could not reach. Further upgrades are planned. New facilities are under construction on multiple continents. If high-frequency gravitational wave detectors follow the same developmental trajectory that LIGO followed, achieving their projected sensitivities within decades rather than centuries, the kilohertz to megahertz band will eventually open to astronomical observation, and when it does, Clough's warp bubble collapse waveform will be a template in the search algorithms, a signal shape to look for, computed from first principles, that no known natural process produces. The implications extend in a direction that Clough's paper addressed carefully, neither overclaiming nor dismissing the possibility. If advanced civilizations exist elsewhere in the galaxy, and if some of them have developed warp drive technology, and if their drives occasionally fail, the collapse events would produce gravitational waves. Those waves would propagate outward from the collapse point at the speed of light, spreading across the galaxy, crossing the distances between stars, eventually reaching Earth. A civilization operating warp drives regularly over centuries or millennia would produce a continuous background of such events, a low-level hum of warp collapse signals embedded in the gravitational wave sky. By searching for the specific waveform predicted by the simulation, astronomers with sufficiently sensitive instruments could potentially detect not just the gravitational waves from astrophysical objects, but evidence of technology, evidence of engineering, evidence that something somewhere has built a device capable of warping space-time, and that the device has, at some point, broken. This is not the search for a radio signal. It is not looking for a laser pulse aimed at our solar system. It requires no deliberate transmission from the civilization being detected. The signal would be an unavoidable byproduct of operating the technology. The way the electromagnetic radiation leaking from our own cities is a byproduct of using electricity, detectable by anyone with the right instruments at the right distance, without any intention on our part to transmit it. A civilization that had never heard of Earth, that had no idea our solar system existed, that was simply going about the business of traveling between stars, would be radiating warp collapse signals into the universe every time one of their drives malfunctioned. And those signals, arriving at Earth after crossing whatever distance separated us from their civilization, would carry a specific waveform that nature does not produce on its own. Sit with that for a moment. The universe has been old for a very long time. The Milky Way galaxy is approximately 13 billion years old. The first stars formed within the first few 100 million years after the Big Bang. Many of the stars in this galaxy are billions of years older than our Sun, which itself formed only 4.6 billion years ago. If life emerges wherever conditions permit it, and if intelligence emerges wherever life has sufficient time and complexity, then some civilizations in this galaxy have had not thousands of years of technological development, as we have had, but millions, hundreds of millions. Time spans so vast that the entire history of human civilization, from the first stone tools to the present moment, represents a negligible fraction of the development time available. A civilization a million years more technologically advanced than we are, if it exists, would be to us as we are to the bacteria that first learned to photosynthesize. The comparison is not metaphorical, it is a reasonable inference from the timeline, and if such a civilization had developed warp drive, had been using it for a million years, had built fleets of warp ships crossing the galaxy on regular schedules, the gravitational wave background produced by their technology would permeate the galaxy. It would be everywhere. It would be passing through the Earth right now, through your body, through the ground beneath your feet, through the entire solar system, as it has been doing for as long as that civilization has been operating their drives. We simply have not had the instruments to hear it. This is one possible answer to what physicists and philosophers call the Fermi paradox. In 1950, Enrico Fermi, the Italian-American physicist who had built the first nuclear reactor beneath the stands of a football stadium at the University of Chicago, was having lunch with colleagues at Los Alamos National Laboratory. The conversation drifted to a recent spate of newspaper stories about UFO sightings, and Fermi made an observation that has echoed through the scientific community ever since. Where is everybody? The Milky Way galaxy contains somewhere between 200 billion and 400 billion stars. Many of those stars host planets. Many of those planets exist within the habitable zones of their stars, at distances where liquid water could persist on a rocky surface. The galaxy is nearly 13 billion years old. If even a tiny fraction of those planets developed life, and if even a tiny fraction of those life-bearing worlds eventually produced technological civilizations, the galaxy should be full of them. Some of them should be millions of years ahead of us. Some of them should have spread across multiple star systems. Some of them should be so advanced and so old that their presence should be obvious, unmistakable, impossible to overlook. And yet, silence. No radio signals from alien transmitters, no laser pulses aimed at our solar system, no megastructures visible in astronomical surveys, no spacecraft in our solar system, no evidence in 70 years of increasingly sensitive searching that anyone else is out there. The universe appears, from every direction we have looked, to be empty of intelligence except for us. This silence is one of the deepest unsolved problems in science. The possible explanations range from the mundane to the terrifying. Perhaps life is genuinely rare. Perhaps the conditions that produced Earth are so improbable that we are the only technological civilization in the galaxy. Perhaps the galaxy is full of microbial life, and we are among the first intelligences to emerge. Perhaps civilizations routinely destroy themselves before they develop the technology to be detectable at interstellar distances, a possibility that our own history makes uncomfortably plausible. Perhaps the physics of interstellar travel and communication is harder than we imagine, and the distances between civilizations are simply too vast for contact to have occurred. Perhaps we are being observed deliberately without being contacted, for reasons we cannot fathom. Or perhaps we have been looking in the wrong part of the spectrum. Clough's paper does not claim to have solved the Fermi paradox. It does not assert that warp drives exist elsewhere in the galaxy. It does not predict that high-frequency gravitational wave detectors will find alien technology signals. What it does is something more careful and more valuable. It opens a new observational window. It defines a signal template. It gives future astronomers something specific to search for, derived from physics, computable from first principles, distinguishable from natural sources by its specific waveform characteristics. Every new observational window that astronomy has opened has produced surprises. Radio astronomy revealed pulsars, quasars, the cosmic microwave background, phenomena that no one had predicted and that transformed our understanding of the universe. X-ray astronomy revealed neutron stars and black hole accretion disks. Gravitational wave astronomy in its first years detected black hole mergers whose masses fell outside the range theorists had expected, neutron star collisions that produced gold and platinum and R-process elements across the universe. Every time we have opened a new window, the universe has shown us something we did not know was there. The high-frequency gravitational wave window has not yet been opened. We do not know what is in it. It might be empty of anything interesting to the question of whether we are alone. It might contain only the signals of exotic astrophysical objects, magnetars, and primordial black holes, and other natural phenomena operating in that frequency. Something with a waveform that matches a template derived from the physics of a collapsing warp bubble. Something that repeats. Something that moves across the sky as its source moves through the galaxy. We will not know until we look. And Clough's paper has told us, for the first time, exactly what we are looking for. The work also produced something immediately useful, independent of any implication for the search for extraterrestrial intelligence. By modeling warp bubble collapse in the framework of numerical relativity, Clough's team developed techniques for simulating exotic space-time geometries that violate the classical energy conditions. These techniques had not previously existed in the numerical relativity toolkit. They required new mathematical methods, new numerical schemes for handling the metric evolution in regions where the energy density takes unusual values. Those methods are now available. They are published in the literature. Other researchers can use them. The techniques developed to simulate warp drive collapse are applicable to other problems in general relativity, where exotic or unusual space-time geometries appear. The interior of black holes, the geometry near cosmic strings, if they exist, the behavior of space-time at very early times after the Big Bang, when the universe was dense enough and hot enough that the classical energy conditions may not have held, the hunt for faster-than-light travel, even if it never achieves its primary goal, generates scientific progress as a byproduct. The Warp Factory software, developed by Applied Physics, is publicly available, used by researchers at universities around the world to evaluate candidate metric families. The classification framework established by Bobrick and Martier provides a shared vocabulary for the field. The numerical relativity methods developed by Clough's group extend the toolkit available for simulating exotic space-time geometries. The energy condition analysis that led to the Fuchs paper has clarified what is and is not physically permitted in warp-drive spacetimes in ways that inform research on other problems in theoretical physics. The pursuit has been worthwhile independent of whether the destination is ever reached. But the destination is not off the table. The window opened by Clough's paper points in two directions simultaneously, outward toward the cosmos, toward the possibility that others have already built what we are trying to understand, and inward toward the laboratory, toward the instruments that will someday be sensitive enough to either confirm that silence or to find, embedded in the gravitational wave sky, something that did not belong to any natural source. 1,000 light-years from Earth, in any of 10,000 directions, there may be a star with planets. On one of those planets, there may be something that thinks, something that has been thinking for longer than our species has existed, something that solved these equations long ago, built the bubble, crossed the distances, and whose drives, occasionally, catastrophically, silently, as far as we have been able to tell, fail. The waves from those failures are moving through the universe right now, at the speed of light, in every direction from their origin, expanding spheres of space-time distortion, carrying the specific waveform of a collapsed warp bubble, crossing the void between the stars. They may already have reached us. They may be passing through the Earth in this moment, through this room, through you, their signal lost in the noise of instruments not built to hear them, waiting for the detector that does not yet exist, but that the physics tells us how to build. Whether those signals are there or not, we now know what they look like. We know their frequency, we know their duration. We know the shape of the waveform that distinguishes them from every natural source in the gravitational wave sky. We know what to build to find them. That is not nothing. In the long history of astronomy, that is almost everything. There is a question that has been present in every line of this journey, stated and restated in different forms, as the physics grew more complex and the implications more profound. It is the question that Miguel Alcubierre was really asking in 1994 when he sat down with Einstein's equations and a memory of starships moving between the stars on a television screen. It is the question that Harold White was really asking when he redesigned the bubble geometry in a NASA laboratory and watched the exotic matter requirement fall to the mass of a motorcycle. It is the question that Jared Fuchs and his colleagues at Applied Physics were really asking when they ran the Fuchs metric through Warp Factory and watched the visualization come back entirely blue. Can we go? Not in the casual sense of whether a particular spacecraft design is feasible or whether a particular mission profile is within budget. In the deeper sense, can the species that evolved on this planet, that learned to make fire and write language and split the atom and detect gravitational waves from black holes a billion light-years away, eventually cross the distance to the nearest star? Can the universe that produced us also be traversed by us? Or are we permanently confined here, sophisticated enough to measure the distances to the stars with extraordinary precision, sophisticated enough to understand exactly why we cannot reach them, but not sophisticated enough to change that fact? 30 years of warp-drive physics have produced an answer to that question. The answer is not simple. It is not clean. It does not resolve into a confident yes or a definitive no. But it is more hopeful than the silence that preceded Alcubierre's 1994 paper, and more honest than the breathless optimism that sometimes surrounds discussions of advanced propulsion in popular science. Let me tell you what the physics actually says. What the mathematics permits is significant and real. Warp-drive spacetimes are valid solutions to Einstein's field equations. This has been established beyond any reasonable doubt since 1994 and has been confirmed, refined, and deepened by 3 decades of subsequent work. The equations that govern the behavior of gravity and spacetime, the same equations that correctly predict the orbits of the planets, the bending of light around massive objects, the existence and properties of black holes, the expansion of the universe. Those equations also permit geometries in which a region of flat spacetime translates through the surrounding universe at arbitrary velocities. The mathematics does not forbid this. It describes it. What the mathematics also permits established definitively by the Fuchs paper in April 2024, is a warp drive built from ordinary matter. The three-region structure identified by Bobrick and Martir, the framework that organizes all possible warp drive spacetimes into a coherent classification, contains configurations that satisfy every classical energy condition without requiring exotic matter with negative energy density. A matter shell with a specific density distribution combined with a shift vector structure that produces the compression and expansion of a warp bubble achieves the warp effect using only the kinds of matter and energy that exist throughout the observable universe. This is not a marginal result obtained by pushing the mathematics to its limits. It is a clean result, confirmed by peer review, published in one of the field's most respected journals, reproducible by any researcher with access to the Warp Factory software. The warp effect is not forbidden. The exotic matter requirement is not universal, at least in subluminal configurations. A warp drive connects to physics we know. What the mathematics also says, with equal clarity, is that superluminal warp travel remains deeply problematic. Every faster-than-light warp configuration yet identified violates at least one energy condition. The horizon problem, the Hawking radiation problem, and the particle accumulation problem are not engineering challenges that better materials or more energy could overcome. They are features of the physics of superluminal travel itself, consequences of what happens to space-time geometry and quantum field theory when a bubble crosses the light barrier. Whether future theoretical work will find a path through these problems, whether quantum gravity corrections will soften the Hawking radiation, whether the solution space identified by recent papers contains superluminal configurations that avoid the worst consequences, nobody currently knows. The honest answer is that the light barrier remains standing for warp drive as it does for everything else, until physics shows otherwise. What the mathematics is genuinely ambiguous about is the territory between here and there, whether Casimir effects or other quantum processes can be scaled up from the nanogram per year production rates of exotic matter in current experiments to the quantities a warp drive would need. Whether new physics beyond the standard model, discoveries not yet made and not yet imagined, might reveal substances or phenomena that change the energy calculus for superluminal configurations. Whether the solution space that recent papers have begun to map more carefully contains hybrid designs that combine the physical reasonableness of the Fuchs result with higher velocities. These questions are open. They may remain open for a very long time. Now consider the distance that has been traveled since May 1994. Alcubierre's original paper required exotic matter equivalent to the mass of the entire observable universe. One paper, 8 pages. A valid solution to Einstein's equations and an energy requirement so catastrophic it seemed to place the concept permanently beyond reach. In 1999, Van den Broek's geometric insight reduced that requirement by a factor of 100 billion, from the mass of the observable universe to the mass of Jupiter, an improvement so large it moved the problem into a different category of impossibility, without yet moving it into any category of possibility. In 2011, Harold White's toroidal redesign with thickened bubble walls reduced it further to 700 kilograms, the mass of a motorcycle. Still impossible because the substance required had never been produced in any measurable quantity, but impossible on a human scale, a scale that belongs to the world of engineering rather than the world of cosmology. In 2021, Bobrick and Martir's classification framework revealed that the entire solution space had not been explored, that subluminal warp drives had been neglected in the focus on superluminal travel, and that subluminal configurations might avoid the exotic matter requirement entirely. In 2024, Fuchs and his colleagues at Applied Physics demonstrated exactly that. A warp drive satisfying all classical energy conditions, using only ordinary matter, subluminal in velocity, physically consistent with everything confirmed by experiment and observation, 30 years, from the mass of the universe to no exotic matter at all for subluminal configurations. That trajectory did not happen by accident. It happened because a small number of careful, rigorous physicists took the problem seriously and worked on it systematically, using the best tools available at each stage, building on each other's results, refining the geometry, mapping the solution space, checking the mathematics against every available physical constraint. The trajectory of that progress is itself a kind of evidence. Not evidence that warp drive will be built, but evidence that the problem is not static. The solution space is being explored. The requirements are being understood with increasing precision. The tools for evaluating candidate designs are improving. The community working on the problem is growing. In 1994, warp drive research consisted of one paper and its immediate responses. By 2024, it had become a legitimate subfield with dozens of active researchers, an international conference presence, computational tools available to anyone, and results published in the most respected journals in the field. The gap between theory and engineering practice is real, and it is enormous. It deserves to be stated clearly rather than papered over with optimism. The matter shell in the Fuchs design must maintain a density profile specified to extraordinary precision under conditions no material we have ever produced could withstand. The energy required to accelerate even a subluminal warp bubble to a significant fraction of light speed is measured in terawatt-hours, energy on a scale that challenges description in terms of any current infrastructure. The instrumentation needed to test warp effects at laboratory scale does not exist at the required sensitivity. We are not decades from a working warp drive. We are not centuries from one, in any confident sense. The timeline is genuinely unknown, which is a different thing from saying it is short. What we can say is that the problem has a structure, it has a shape. The requirements are understood well enough to know what must be solved and in what order. The theoretical foundation is solid. The classification framework is established. The first physical solution has been found. The gravitational wave signatures of warp drive operation have been computed. The search template exists. The field has the tools and vocabulary of a mature research program, even if the engineering is centuries away. That is not where physics stood in 1993, before Alcubierre wrote his paper. Before his paper, the question of whether warp drive was consistent with general relativity had not been answered. The answer might have been no. A rigorous no-go theorem might have emerged from the analysis, closing the question definitively. It did not. The answer was yes, with conditions, and 3 decades of work have refined those conditions with increasing precision. There is something worth sitting with in the history of this problem, something that the dates and papers and energy requirements do not quite capture on their own. In 1905, Albert Einstein was a patent clerk with no academic position, publishing papers in his spare time that nobody had asked him to write, working on problems that his contemporaries considered either solved or intractable. His special relativity paper established the cosmic speed limit that has constrained every propulsion concept since. He did not intend to imprison humanity in the solar system. He was following the mathematics where it led, with the confidence that the universe was comprehensible and that careful reasoning would reveal its structure. In 1915, Einstein completed general relativity. The field equations that Alcubierre would use 79 years later to find the warp metric were written down in their final form in November of that year. Einstein never considered using them to look for faster-than-light travel. The thought, as far as the historical record shows, never occurred to him. He was interested in gravity, in the large-scale structure of the universe, in whether the cosmos was static or expanding. The idea that those equations contained, hidden in their mathematics, a geometric loophole that might someday allow a spacecraft to cross from one star to another, would likely have seemed to him an extraordinary speculation. In 1994, Alcubierre found that loophole, not by accident, by asking a specific question and following the mathematics carefully. The question was inspired by science fiction, by a television show that had no scientific pretensions and made no attempt to explain its technology. The answer was a valid solution to the most powerful gravitational theory ever written. In 2024, Fuchs and his team closed the question of whether warp drive required exotic matter, at least for subluminal configurations. The answer was no. The result emerged from 3 years of systematic work by a small private research group operating in an office building in Midtown Manhattan funded by investors who believed the problem was worth attacking, and staffed by physicists who were willing to spend their careers on something most of the world considered science fiction. The story of warp drive physics is not primarily a story about spacecraft. It is a story about what happens when human beings take an impossible-sounding question seriously and follow the mathematics wherever it leads, for as long as it takes, without knowing in advance whether the destination will justify the journey. The destination, so far, is a subluminal warp drive that exists only on paper, requiring matter shells we cannot build and energy levels we cannot produce, but consistent with every law of physics we have confirmed. It is a door that is open, not a door we can walk through today, or tomorrow, or in any time frame that feels personally relevant to anyone alive right now, but open. The distance from the first controlled-powered flight at Kitty Hawk in December 1903 to the first human being standing on the surface of the moon in July 1969 was 66 years. 66 years from a 12-second hop 12 feet above the sand to bootprints in the lunar regolith. The people who watched the Wright brothers fly that morning did not live to see the Apollo program. They could not have imagined it. The technology required did not exist. The mathematics required had not been fully developed. The materials science, the computing, the rocket propulsion, none of it was available in 1903. And yet the trajectory from one to the other, in retrospect, was not discontinuous. Each development built on the previous one. Each breakthrough opened the next question. The process was not inevitable, but it was not random either. It was the result of sustained attention from people who believed the problem was solvable and worked on it systematically across generations. Warp drive may require not 66 years but 600 or 6,000. The timescales are genuinely uncertain in a way that the timescale from Kitty Hawk to Apollo was not. The engineering challenges are more fundamental, touching the limits of materials, science, and energy technology in ways that airplane development did not. The physics, while permitted, is not yet understood well enough to specify what a working device would look like in any detail beyond the mathematical description of the metric. But the question has the same character as the question the Wright brothers were answering, not whether a thing is possible, whether we can figure out how to do it. Return now to where this journey began, to the number that started everything, 25 trillion miles. The distance to Proxima Centauri has not changed. It will not change on any timescale relevant to human civilization. The stars are where they are, separated by volumes of space that dwarf every scale of human experience, every measure of distance that evolved minds developed on the surface of a small planet, orbiting an unremarkable star in an outer arm of a middling galaxy. 70,000 years at Voyager's speed, 4 years at the speed of light. The fastest thing the universe permits, traveling without rest, takes 4 years to cover that distance. And yet, the equations that describe that universe also describe a geometry in which a region of spacetime can translate to any destination at any velocity, carrying its contents without accelerating them, consistent with every physical law that has been tested by experiment. Those equations were written down in 1915. The warp geometry they contain was identified in 1994. The exotic matter requirement that seemed to make it impossible was reduced by 20 orders of magnitude by 1999 and eliminated entirely for subluminal configurations by 2024. The progress is real, the direction is clear, the destination is uncertain in its timing but not in its character. Somewhere in the future, in a laboratory or a research group or a theoretical physics department we cannot yet identify, someone will solve the next piece of this problem. We'll find the geometric configuration or the physical mechanism or the theoretical insight that moves the solution space in the direction of the stars. As others solve the pieces before them, and as others will solve the pieces after. The universe did not have to be this way. It did not have to be a place where the same laws that separated the stars also permitted, in the deep structure of their mathematics, a way of crossing those separations. It did not have to be a place where the same species whose entire recorded history fits into a fraction of the cosmic timescale could develop the instruments to measure gravitational waves from black holes, 1 billion light years away. and develop the theories to write down the geometry of a warp bubble, and develop the computational tools to evaluate whether that geometry was physically real. It is, though. That is what the last 30 years of physics have established. The universe is the kind of place where these things are permitted, where the mathematics opens doors that the engineering has not yet learned to walk through. That is not a small thing. In the long run of cosmic time, it may turn out to be everything. The distance to Proxima Centauri is 25 trillion miles. A species that detected gravitational waves from the collision of black holes a billion light-years away, that photographed the shadow of a supermassive black hole at the center of a distant galaxy, that built an instrument sensitive enough to measure a change in length smaller than a proton across 4 kilometers of steel and glass, that wrote down the geometry of a warp bubble from first principles, and then spent 30 years removing every physical objection to building one. That species does not give up on a problem because the numbers look hard. There is a moment, sometime in the hours before dawn, when the atmosphere is cold and clear, and the light pollution from the nearest city has faded enough that the stars appear as they actually are, not the handful of bright points visible from a suburban backyard. The full sky, the Milky Way as a structure, its billions of constituent suns resolved from a smear of light into something almost granular, almost textured, stretching from horizon to horizon in a band that contains the center of the galaxy and the trailing edge of one of its spiral arms. If you have seen that sky, you know the feeling it produces, something between vertigo and reverence, the sudden awareness of scale, of distance, of the improbable specificity of the position you occupy in a universe that extends in every direction so far beyond comprehension that comprehension itself feels like a kind of audacity. Every star in that band is a sun. Most of them are orbited by planets. Some of those planets exist in the conditions that allow liquid water to pool on a rocky surface. The distances between them are measured in years of light travel time, in tens of thousands of years, at the velocity of the fastest machine we have ever built. And somewhere in the mathematics of the universe that produced that sky, that produced those stars and those distances and the empty light years between them, there is a geometry. A solution to equations written by a patent clerk in Bern in 1905 and completed by the same man in Berlin in 1915. A geometry in which the distance does not have to be crossed in the conventional sense, in which a pocket of space-time can be moved from here to there, carrying its contents, without asking the contents to move at all. The geometry is real. The physics permits it. The engineering is centuries away, at minimum, possibly more. The problems that remain are enormous. The timeline is unknown. The outcome is uncertain. But the door is open. It was opened in 1994 by a 28-year-old physicist who watched Star Trek and asked the right question. It has been held open, gradually widened, its frame reinforced by 30 years of careful work, by the researchers at NASA's Eagle Works and the Free University of Brussels and the Applied Physics Laboratory on the 47th floor of a Midtown Manhattan office building and Queen Mary University of London and every other institution where someone decided this question was worth taking seriously. The stars have waited 4 billion years for something on this planet to notice them. They will wait a while longer. They are not going anywhere. And neither, it turns out, is the mathematics that describes how to reach them. The door is open, the hallway is long, and somewhere ahead, past the materials challenges and the energy requirements and the instrumentation gaps and the decades and centuries of work still remaining, the first warp bubble is waiting to be built, waiting in the equations, waiting in the geometry, waiting in the patient, indifferent, extraordinary mathematics of a universe that turned out to be stranger and more generous than it had any obligation to be. You are alive at the moment when the door was found. That is not nothing. That is, in the full weight of everything this journey has shown you, almost everything.